I would like to welcome Dr. Baichun Wang to present the first presentation. This is done remotely. The topic of the presentation is towards human-centric smart manufacturing. Baichun, the floor is yours.
Yeah, thank you for Professor Wang's introduction. The voice and the video is clear?
Yes.
Yes, okay, I will begin. So, hi everyone. Good morning, good afternoon, and good evening. This is Baichun Wang from Zhejiang University. Today, my topic is on the human-centric smart manufacturing. As we know, the intelligent manufacturing is also called smart manufacturing, is a general and big concept, and its content is also in the expanding with the integration of advanced manufacturing technologies and information technologies. So, in the past decades, there are many related concepts like the flexible manufacturing, the cloud manufacturing, the social manufacturing related with smart manufacturing. At present, especially in recent years, the smart manufacturing is entering a new generation due to the rapid development of emerging technologies like the mobile internet, the big data, the cloud computing, and AI. So we can see the content of smart manufacturing is still evolving, but the goal is not changing. It's about the quality, about the efficiency issues, about the cost, and the competitiveness. Also, from the system perspective, we can understand the smart manufacturing as the integration of physical systems, the cyber systems, and the human systems. So we call it the human cyber physical systems, HCPS. So in this perspective, the essence of smart manufacturing systems can be understood as the design, the construction, the application of HCPS at different levels for a different purpose in the design, in the production, in the maintenance and service. So my talk today covers three sections. The section one is about the technology system of HCPS for smart manufacturing. In the left picture, we can see the architecture of smart manufacturing can be understood from the HCPS perspective. Also, the overall architecture of smart manufacturing can be described from three dimensions, as shown in the right picture: the value dimension, the technology dimension, and the organization dimension. So when we talk about the value dimension, it means the value creation and the value optimization is the main goal of smart manufacturing. The value creation and value optimization can be realized through the product design, also called the product innovation, the intelligent production, also called the product production innovation, and the intelligent service and their integration. So as a large and general system, smart manufacturing includes the three function systems and the two supporting systems. The three functional systems means the intelligent products, the intelligent production, and the intelligent service. The two supporting systems include the intelligent manufacturing cloud and the industrial internet. The second dimension means the organization dimension. When we talk about the organization dimension of smart manufacturing, it means the organization and the implementation of smart manufacturing. It also covers three levels: the unit level, the system level, and the system of system level. For example, in the unit level of HCPS, the human is one of the key technologies consisting of human-machine collaboration technologies, such as the human factor engineering, the extended reality, the human-robot collaboration. So the right picture shows the extended reality, XR. The second dimension means the technology dimension. It is from the perspective of technology evolution of smart manufacturing or intelligent manufacturing. It can be divided into 3 stages or 3 models, which means the digital manufacturing, the digital network manufacturing, and the new generation intelligent manufacturing. They are also known as 3 basic paradigms. So the above introduce the technology system of smart manufacturing from the HCPS. Also from the HCPS perspective, we propose the idea of human-centric smart manufacturing in recent years. The reason we propose the idea of human-centric smart manufacturing include various aspects. The most important one is that the human are the main target of the service of smart manufacturing. With the help of new technologies, especially the production and the service technologies, smart manufacturing can provide with humans, the consumer, with various types of products and service. So this is the main reason. The second one is that the human also have a critical role in the implementation of smart manufacturing or smart factories. For example, Elon Musk in 2016 said the Tesla's factory will be an alien dreadnought by 2018. He said you really can't have people in the production line itself. But 2 years later, in 2018, Elon Musk said on the Twitter, it's a mistake. So this is a good example. The other reasons include the human role. For example, in the industry 5.0 and the society 5.0, it shows that the humans will also have a more important role in the future development of manufacturing systems and the future societies. Also, even though we can see a lot of factories can be completely automated, but not all the industries and factories need to be completely automated, especially for the small and medium enterprises. We should also think about the technological and economical viabilities when promoting the smart manufacturing. So the above are the reasons why we propose the idea of human-centric smart manufacturing. When we talk about human-centric smart manufacturing, we also can understand the concept from 4 dimensions, including the product, the production, the model, and the foundation. The foundation means the human cyber-physics systems and the knowledges in human fact engineering. The other main functions include the human-centric intelligent products, the human-centric intelligent production, and the human-centric transformation of an industry model. Let's go to the first one, the human-centric intelligent products. In this context, the concept of human centricity means the intelligent products should fully consider the needs of the humans and the human factors at the very beginning of the design process, especially for the products directly facing large groups of consumers. The Xiaomi smartphone is a good example, which is a Chinese company. And also for the design of the industrial equipment, the possible human intervention should also be considered to provide the necessary space for the designers and the engineers. All of this means the human-centric in the products and in the equipment. The other one is about the intelligent enterprise. When we talk about the intelligent enterprise, it includes the design of the product, the manufacturing of the product, and the management of the product. The application of human-centric intelligent production includes the human-machine design cooperation, the human-machine collaborative assembly, and the human-centric management. Let's also take the human-robot collaboration as an example. This picture is from the paper by Professor Li Huiwang. is a very good example for the human-centric intelligent production. Also, when we talk about the human-centric transformation of the industrial model, it means the transformation from the product centricity to the user centricity, from the large-scale production to the customized production, and from the production-oriented manufacturing to the service-oriented manufacturing. The example is also from a Chinese company, the Haier. Haier's cosmic flags shows the human centricity and the customized production in the production process. So it's a very good example for the human-centric transformation of the industrial model. So the above slides show the idea and the examples of human-centric smart manufacturing. But as we know, the human-centric smart manufacturing is in the very early stage, so there are many challenges in the future. The main challenge comes from three directions: the system modeling, the knowledge engineering, and the human-machine symbiosis. When we talk about the system modeling, it means it's a very important technology for the CPS and the digital twin. In the past decades, we have learned a lot in the mathematical modeling to reveal the objective laws of the physical systems, but it is not enough to handle the highly uncertain and complex issues in the smart manufacturing systems. And in recent years, the big data-driven intelligent modeling is emerging, and it can solve the issues which cannot be solved by the mathematical modeling. So in theory, a hybrid modeling based on the integration of mathematical modeling and big data-driven intelligent modeling can improve the modeling quality of the human-centric smart manufacturing systems, but it also remains as challenges. The second one comes from the knowledge engineering. The smart manufacturing system can also be understood as the activity of the engineering, of the knowledge engineering in the manufacturing systems. It covers major groups of challenges from three directions. Challenges one is lying in the manufacturing domain technologies. For example, how to continue to achieve innovation in the diverse aspects such as design, the production, the service, and the maintenance. Challenge two comes from the intelligent technology, which is also known as enabling technologies. For example, how to achieve steady improvement in the universality, stability, and security. The third challenge comes from the integration of manufacturing and information technologies. For example, how to develop and advance manufacturing domain technology by using the intelligent technologies. So this is about the challenges from the knowledge engineering. The last main challenge comes from the human-machine symbiosis. From the picture, we can see the smart manufacturing based on the HCPS calls for humans to take a greater role in order to form a human-machine symbiosis. But it also will bring many challenges. For example, how can the effective division of work and cooperation between humans and intelligent machines be achieved? How the human intelligence and the machine intelligence can be utilized and especially inspired by each other to get the human-machine hybrid intelligence is a challenge. The other example is about the safety, the privacy, and other issues. How can this be addressed, which may be introduced by AI and smart technologies? So the above are the three main challenges. In summary, in line with the ancient Chinese concept saying the harmony between humans and nature, 天人合一 in Chinese, there should be close cooperation and collaboration between humans and sapiens, for example, the intelligent machines, in order to realize the smart manufacturing system at the harmonious state For example, the human-centric smart manufacturing, in order to move this technology forward for the humankind's benefits. This is also a main idea comes from the Industry 5.0 concept. So as we know, it's in the very beginning stage for human-centric smart manufacturing. So last year, by the help of Professor Li Huiwang, we organized a special issue on Journal of Manufacturing System. The title of this special issue is on human-centric smart manufacturing, trends, issues, and challenges. There are 126 submissions, and finally, 41 publications published. It covers several topics, such as human-centric assembly in future factories, the production planning in MR, and the architecture for the cooperative engine in the process control. Also, the human-machine collaborative additive manufacturing. We can say there are many different areas in this emerging area. So above slides are my talk today. Thank you for your attention. If you have any questions, please feel free to contact me with the email. My email address are baichunw@zju.edu.cn. Thank you.
Thank you, Baichun. So Baichun's talk today is centered around human centricity in smart manufacturing. We still have 8 minutes left. If you have any questions, please ask a question directly to Baichun. For online participants, you can use your chat box. Hopefully, our staff here can help to read your question.
Question.
Yes, please.
I'm just curious, what sort of focus, did you do any focus groups in order to get data around the human centricity? So should I repeat it?
Yes.
Sorry?
So the online
Yeah.
participants group.
So can you elaborate a little bit more whether if you did any focus groups to understand the impact of the human-centric work that you presented?
You mean the data?
Yeah.
Yeah. So there's a main problem in the implementation of human-centric smart manufacturing because of the diversity of the data of humans and machines are the main challenges in the future development. For example, how to establish the digital twin model of humans based on the data acquisition, and how to use this data to predict the human's motion in a research area.
Yeah, I think there's some research on neuroscience where they've been able to take the unstructured data that typically human beings provide to a more structured based on variables, certain segregation and labeling. I mean, maybe we can take that offline, but I'm happy to discuss. I'm very curious about that.
Okay.
Another question from my side is, how do you think that in the future AI can help in human-centric smart manufacturing? You talked about knowledge engineering, perhaps partially included. Specifically, how the AI can contribute and in the long run towards the smart manufacturing and sustainable manufacturing. Maybe you can elaborate more, please.
Yeah, that's a good question and also a good suggestion. So from my understanding, the understanding of the human itself based on the AI technology is a very interesting topic. How, for example, when we use the AI technologies, we can predict the human's motion and the human activity in the human-robot collaboration. Also, when we talk about the knowledge engineering, we can use the big data of the activity knowledge in the manufacturing system to predict the understanding and the design of the products. Yeah, does this make sense?
Yeah, I think so. And especially when we talk about sustainability, there's one dimension is societal sustainability. From that aspect, human-centric smart manufacturing, if we can assist the human, we make the human working environment sustainable, that contribute to sustainable manufacturing, at least from one aspect. Perhaps AI can also help in decision-making in different areas, planning, control, monitoring, that also contribute to the saving of a cost, the time, and the environment, in a sense, resource efficiency. So I think that's a role that AI can play.
Yes, I totally agree. And the other side, the one dimension is from the product sustainability. The other dimension can come from the human sustainability, such as you mentioned the skills and the lifelong learning based on the AI for humans. Also is one dimension of the understanding of the sustainability. Do you agree?
Yeah, thank you.
Thank you.
Do we have any other question in the room and online? Is there any questions online posted?
Let me see. Have a see. No,
yeah, if not, we can move on. Thank you, Baizun, for your presentation remotely. Thank you.
Thank you, Professor Wang. Bye-bye.
We will move on to the next presentation. The next presentation will be given by Malur Narayan. Let me briefly introduce our speaker first. Malur is the Vice President, Emerging Technology, Sustainability, GTM, Tata Consultancy Services, Technology Business Leader, ESG, Mentor, Diversity Champion, Mental Health Advocate. Malur Narayan is a proven technology business leader with over 2 decades of experience in technology industry, having worked in 5 countries and presently leads the sustainability GTM for Tata Consultancy Services across North America. He brings an effective contribution of a corporate and entrepreneurial experience, having held a broad range of senior management role at Notel and Tata, covering product engineering, sales, business development, and product management. The topic of Malur today is on use of neutral network in supply chains and generative AI models for resource management. Malur, the floor is yours.
Thank you, Professor Wang. Good afternoon, good morning, everyone, and wherever you're in the world. Thank you for the introduction. Today I'm going to be talking a little bit about the concept of neural supply chain and how it's applicable to both sustainable manufacturing as well as in terms of being using the combination of reinforcement learning and generative AI in areas such as supply chain modeling and business modeling. So I'll talk a little bit about that. I invite you to imagine, a world where machines can learn from experience, adapt to new situations, and make decisions based on data. A world where supply chain is optimized, and we all know the impact that the latest pandemic has had on supply chain over the last 3 to 4 years, and other black swan events that could disrupt. So I think it's very important to have use technology to advance those two areas, not just in terms of sustainability, but also in terms of growth and improving costs and make the supply chain itself viable. Next slide, please. I know I was introduced by Professor Wang there, but I just wanted to give a little bit of background about my experience in AI and machine learning. Dates back to almost 30 years ago when I was involved in building the adaptive set training algorithm, which is a reinforcement learning early methodology using neural networks to build and control systems. So based on, I've kept up with that, and now we have the ability to be able to use many of those technologies with the advent of cloud, sensors, IoT, etc., to be able to use a combination of those technologies to effectively drive some of the benefits that that I'll talk about today. Next slide, please. I want to just present a picture of the macro climate. VUCA, or VUCA, is an acronym which stands for volatility, uncertainty, complexity, and ambiguity. And essentially, these are the qualities that make a situation or a condition difficult to analyze or respond to. Understanding how to navigate these is very critical for businesses and manufacturers, and can greatly improve the strategic abilities of companies and lead to better outcomes. One of the big challenges we have, we are dealing with VUCA. We have ESG, which is a hot topic right now across both environmental, social, and governance. And combine that with the present day challenges around inflation, labor shortage, financial regulation and compliance, and of course, supply chain challenges. All of those are causing significant demands, and therefore, both in terms of an increasing number of customers are now companies are now requiring on-demand, eco-friendly solutions that are more aligned to a circular economy, while still being able to provide, the cost benefits and the growth challenges that come with running an efficient supply chain. Next slide, please. I want to talk about some metrics here. So industrial manufacturing accounts for over 20% of greenhouse global gas emissions. Over 54% of the world's energy consumption comes from manufacturing, and 7 billion tons of solid waste just in the US alone. And globally, that's 4x or 5x of that. These metrics and statistics clearly emphasize the urgency and the need for sustainable transformation in manufacturing processes, so that we can mitigate the environmental impacts, reduce resource consumption, and promote more circular economic practices. And delving specifically into supply chain, you can see that the supply chain has a significant impact on the overall economy, right? An example was Boeing, when they first introduced 787 aircrafts, they grossly miscalculated the initial demand for it, and which ended up in a 3-year delay in being able to release the product. So that can cost the business a substantial amount. So manufacturing supply chains involve not just, the impact of that is beyond just the facility itself. It includes transportation, logistics, and which drive carbon emissions from a variety of different end-to-end processes. And the same thing as far as the carbon footprint is concerned. The product, the carbon footprint of those products extend beyond the manufacturing facility as well. Right from the downstream processes to the upstream processes. So automating, integrating, and de-risking the supply chain is one of the key drivers to maintain sustainable manufacturing growth. Next slide, please. There's I've been hearing for the last 15 years that data is the new oil. Well, that's old news now, and AI is the new refinery, because data is only data, and there's lots of it. The quality of data is more important than the quantity of data, and therefore how you use it. This is an original quote from me, by the way. So, and AI is a new refinery, and how you use that is very, very critical. Next slide, please. So let's talk a little bit about how neural networks impacts, how we can make the future of manufacturing more neural. Neural networks are, for those, you're all, this is a machine learning workshop, so I don't need to explain it, but they're a typical type of AI where that are inspired by the human brain, just with neurons and a network of nodes, which improves the brain's learning process. So neural networks are very similar in that regard. They're specifically suited well to pattern recognition, making them suitable for things like demand forecasting, inventory optimization, and route optimization. And they're very good at analyzing historical data and taking the future data and data from existing processes and being able to correct itself. And they lend itself very well to a use case like this. You can see here there's a number of components to manufacturing, and traditionally, manufacturing has been a very siloed, supply chain has been a very siloed individual processes where they're either not connected, disjoint, very fragmented, or decentralized. And the power of AI and neural networks is to be able to provide a more connected, real-time, and automated, responsive, self-correcting or self-regulating algorithms which can take action without human intervention, and that's the power of that. I think I kind of covered the next slide as well. If you look at how the present day, a lot of the manufacturing is linear, sequential, and very siloed, as I said before, reactive, intuitive, and requires significant manual intervention and manual responses. So augmenting the supply chain through digital solutions, including neural networks, machine learning, and at the same time, being able to use the power of cloud and IoT sensor data is very, very critical, in being able to provide a more cognitive, connected response. This slide, I want to talk a little bit about what an architecture of a neural supply chain looks like. It's a busy slide, but I want to talk a little bit about, on the left-hand side, what drives the behavior of a supply chain. In terms of shift in consumer behavior that we're seeing today, the advancements of technology, changing face of the highly competitive environment, newer business models that have not existed for many years, significant market disruptions, black swan events, and the never-ending requirement to shrink the time to market for products and to be driven. So all of that combined with the sustainability SDG requirements around a more circular product and driving more circularity in your products requires you to think differently and move away from the more traditional models. And here you can see there are three sort of layers that combine a combination of technologies that you see in the purple, that drive specific types of behaviors, such as continuous intelligence, personalization, automation, etc., that eventually take you to a much higher layer, abstract layer, where the entire the system is more cognitive, collaborative, and connected. So how can enterprises benefit? How can manufacturers benefit from neural capabilities? I think there are three big areas of impact. Obviously, more adaptive, because change is constant, and to be able to And in a manufacturing environment, a supply chain environment, there's constant change, uncertainty and unpredictability of real life situations where a truck breaks down or a ship breaks down or a supplier goes belly up. To be able to manage those variability and plan for contingencies dynamically without having to necessarily always plan ahead for it is very, very critical. The second one is autonomous operations, kind of as a segue from the first areas of impact. So using the being able to engage with smart connected assets, because the world around supply chain is also going all digital and sensor based. You want to be able to connect with all those external systems and without any friction and quite seamlessly in order to be able to utilize all that data to drive minimal human intervention. And the third one, is self-explanatory. I talked about this. There are four core technologies that are in the neural supply chain: IoT, visualization using XR, AI, and of course, a cloud. What are the skills that are needed for companies and manufacturers to be able to build the neural networks of the future? You will see there's fundamentally three categories here. Foundational skills, such as, being programming skills, basic skills around core engineering, procurement, supply chain management, data analysis, material sciences, etc. And then more, the intermediate skills are more around using those core skills and building on that, where a bit more specialization around computational thinking or IoT, big data analytics, advanced programming, etc. And then at the top are some of the newer technologies that are coming into play that require, more advanced skills. A combination of those are what companies will have to build. So how can a manufacturer start adopting neural? I don't want to spend too much time on this, but aside say this is, there are 5 stages of this. You want to align your core business strategy around digital and business. Many companies are now getting started on their digitization of the supply chain. So, and then your product development strategy needs to reflect those neural characteristics in terms of planning around the feedback loop, planning around self-regulation, and creating a self-aware process. And so, that requires you to restructuring whatever existing processes, operating models you have. And we talked about the skills in the previous slide about, what types of skills are required. And then a more customized approach specific to your type of business around what are the nodes that you need to build within your neural network. We've created like 3 stages of maturity in neural adoption. There are essentially, and based on 5 parameters: predictive, leveraging data, continuous intelligence, collaboration, and automation. And there are 3 categories. The neural ready is where most of the companies are today. Probably 90% of the companies, manufacturers are in that stage, which still requires extensive manual effort, very, very operational focus, mostly on demand, driving your supply chain on demand. And yes, there's some AI and automation, but they're not necessarily connected with all the external systems. And then I'd say probably some companies, the early adopters, are into the adopting neural phase, where a large part is automated, and they have agreed upon interfaces and protocols between external systems with their suppliers as well as their partners, and driven by tools and man-machine interactions. I think the holy grail, of course, is the neural and self-acting, which we've proven. I'll present a couple of case studies where we have gotten to that, at least in some sections of supply chain. So typically enterprises who want to get to the neural and self-acting from where they are today have two ways of going about it. Either you go through, there's what we call the capability augmentation, which is focused on at the beginning largely on internal and limited to the internal enterprise's capability itself. And there, the organization can explore and adopt various neural aspects along with procurement, warehouse, inventory management, transportation, logistics, which are key functions. These are well suited for companies that have fewer suppliers, where the focus is on more quick wins and low lead time, where the investment is relatively lower. The second one is more around ecosystem focused, where you are dealing with your entire value chain of partners and taking your current capability level and also augmenting the capability level of your the ecosystem partners, which is a longer road. Next slide, please. And the readiness of, if you look at where we are today with the readiness of supply chains, I talked about how most companies are either between neural ready and neural adopting. A lot of it really depends on your specific business model and your product that you're building, and requires a fair amount of shift in your capability from one stage to another. Next slide, please. So let's talk a little bit about the use cases, right? A neural supply chain can offer numerous benefits, as we saw, to manufacturers, right? Ranging from purchasing, where processing inputs from prevalent market conditions combined with supply chain aspects, such as forecasting, demand, and planning, can really help drive purchasing departments of enterprises. Then the logistics is another element, inventory and warehouse management, and transportation. And I want to delve a little bit into the types of AI, where we're using AI in sustainable supply chain and manufacturing. The areas are specifically around predictive maintenance. We talked about supply chain optimization, resource recovery and reuse, environmental impact, energy optimization, and last but not least, lifecycle assessments, when going from end to end and looking at where you are today and how you need to get to your SBT targets at whatever target, net zero targets you've achieved, you outlined for you. So we did for a logistics company, we did a very large transformational program with the neural supply chain concept. And what we did was use we used a combination of different things, where we looked at we used a reinforcement learning algorithm for inventory and route optimization. This is a company that had a significant problem in terms of taking their concrete and cement to the last mile, and because of the type of harsh environmental conditions that they were dealing with, managing the trucks, making sure that the payload that they were carrying doesn't expire because it has a shelf life, and the routes are not available on Google Maps. So you need to be able to use historical data to optimize the route and get it right on time to the end point. And so we used a reinforcement-based algorithm for that, and it interacted with the delivery management system, receiving feedback on efficiency and selecting the routes and adapting its decision-making process accordingly. And you can see some of the results there. We had 15% reduction in inventory holding costs, 20% decrease in transportation costs, and a few other metrics there. And the concept here is really using what we call a multi-layer perceptron neural network, which is a multi-layered neural network, which has a single input layer, an output layer, and multiple hidden layers in between. The benefit of that is that you're able to provide multiple inputs and outputs internally with nodes. This is the next, this one's more around a manufacturer of high voltage electric circuit breaker. Is facing inefficiency and quality problems due to poor supply chain visibility, not being able to look at have an end-to-end view, and especially of many of the raw material suppliers, feeder factories, manufacturing, and customers. So to be able to use sensors across those different inputs and be able to, this is the partner ecosystem model that I talked about, making sure that they are feeding all their inputs and then using machine learning heuristics to capture that data and predict what changes could occur and making recommendations was tremendously useful here. This is another, the next one is a use case with the automotive manufacturer. Next slide, please. Where we utilize the value chain mapping in addition near real-time data to look at a variety of the things like inventory, demand, capacity, etc., and be able to model that whole thing with a neural network. This has significant benefit in terms of being able to reduce your risk, especially for a large automotive manufacturer. This can be very, very critical in terms of lead times and supply times, and the ability to be optimize and predict that without having manual and requiring manual intervention is significant. And then the fourth one is something that is in progress, but is in the works. Something I've also been personally involved in is the generative AI and reinforcement learning based business application modeling. So here's a case where we have a manufacturer that is looking for, has a variety of industrial materials, engineered materials, and they're looking to see how they can use the same material for multiple applications. Today, a lot of that happens by serendipity, where somebody goes to a research conference, they talk to somebody and say, hey, you know what, this material has great thermal properties, silicon carbide or whatever it might be, and you can use that for another application here in maybe building rockets or whatever. And a lot of that happens purely by chance. So you can use AI and generative AI to build a very comprehensive model that does automated business modeling for you, and taking looking at the materials, the existing list of materials, and being able to say, hey, this particular material may have a 90% match for this particular industrial application, and being able to predict what the accuracy of that would be, and so that the amount of time required for discovery and actually pursuing that application and building a proof of concept is dramatically reduced by, instead of 2 years, to maybe 2 months. So the next slide, please. This actually shows how we're building this, from the building a materials repository to scanning, thousands and thousands of research reports and web data, and being able to use generative AI to create intelligent prompts, to use intelligent prompts to be able to aggregate all of the data into something that any business user can use and say, hey, here's an application, here's a material I have, here are the applications I'm looking for. This is just a snapshot of what we're trying to build, something similar. Next slide, please. So to summarize, I think neural networks, adaptive reinforcement learning can be applied in supply chain management in a variety of different cases, as I just showed. We have the ability to streamline processes and improve efficiency, revolutionize the way the companies approach supply chain, optimize production processes, identify inefficiencies, and increase productivity, and sustainable goals such as reducing energy consumption, carbon emissions, and finally, optimal use of resources, which are all fundamental to having a circular economy and reducing environmental impact. I'll summarize by just saying, I think companies are looking for to augment supply chain capabilities through digital solutions, as I explained, building a cognitive, collaborative, and connected neural supply chain, which is the holy grail, can go a long way in de-risking as well as optimizing cost and making it more sustainable. That's it for my talk. Thank you.
Thank you, Marua. Very interesting talk. So the core message I took, you mentioned, is the future of manufacturing is neural. You provided detailed treatment use cases and how to reach there through neural network. This is a very interesting topic. Any burning questions from the audience? Yes, please.
First of all, thank you very much for the presentation, and I love your quote in there. Very
If you're going to use it, please quote me.
That's what I took the photo of the last one. For the cost of implementing a neural solution, have you done any research or any study about the cost versus the benefit, especially for some manufacturers who are still starting from the beginning?
Yeah, a lot of the challenge is around, going back to the quote, a lot of the challenge is around data, right? How the quality of data and the timeliness of the data that you get from a variety of sources, because as I said, manufacturing processes involve so many different touch points, both internal to the company and external to the external parties. And they're all come in different formats. So a large part of the cost actually involves data cleaning, data synthesization, and ensuring that the data is usable by the neural network. Building the neural network itself is not as hard as ensuring that the data is in the right format, and that happens. The other part of the cost, which is usually a stumbling block for many companies, is the digitization. Many companies don't even have the infrastructure set up yet, right? The cloud infrastructure, data infrastructure that you need in order to be able to centralize a lot of the data and process it, or even at the edge endpoints, at the edge of the network. So those are things, but what we normally tell many of the companies when we talk to is to take it one step at a time, right? Find the most critical elements that are taking the largest, that are going to be most critical to your business in terms of risk, in terms of, and then try and address that to start with, and then progress rather than try to do everything at once.
And did you conduct any like numeric cost actually to try and?
Yeah, I can share some with you.
That would be great.
I'm happy to share that with you. I don't have it here, but
Perfect.
thanks.
You.
Another related,
sorry.
yeah, go ahead.
Hi, thank you for a very interesting talk. I have lots of questions, but in the interest of time, I'm going to only choose one. So I think the best one I had is you might be best suited to answer a question relating to KPIs for using neural networks in smart manufacturing and in AI in general, because I personally work with neural AI for good fields, and I find it very hard to come up with good ESG KPIs to measure against. Obviously, one that you can choose is carbon emissions or something like that. But have you come across any other generics that are useful in smart manufacturing and beyond in AI in general?
I mean, the ones that we typically use are because there are multiple types of KPIs, right? There's the KPIs that you report to agencies, that you report to the market, that you report to whatever regulatory bodies that you are working with. Those are, I think, more from the perspective of, hey, what is my lead time? That's one KPI. How am I improving that from X to Y, X minus 10%, X minus 30%? That's a great. From a business point of view, that's the most vital KPI. How much are you reducing the lead time? How many supply chain disruptions have you had over in a particular cycle? Or what percent of your supply chain trigger actions did not require human intervention, right? So those are some of the things that we do. Obviously, there are some KPIs that are much more lower level in terms of monitoring, performance monitoring of individual plants or boiler stations or what have you, depending on what type of company you have. I don't know if I answered your question, but I can also give you more around the neural network itself, what the KPIs are, but I'll follow up with you offline. Thanks.
Thank you. Because of time, I save my question for later.
I think Jin had a question. So.
Yeah, sorry.
Hello, thank you for the great presentation. You talked about the, I think the neural readiness for the supply chain. So I would like to know, are there some approaches or methods to systematically assess the maturity or the neural or readiness for the supply chain? Thank you.
Yeah, there are about 3 or 4 elements we use in terms of readiness. One is the data infrastructure. You have the digital infrastructure that you have in each of those plants across your company, across your manufacturing facilities. Are they all connected? How's the data, the network, the storage, the compute powers, and the various sensors across your different facilities. So obviously, digital infrastructure and IoT infrastructure is very key. And then resources, we talked about skill sets that are required, right? How are you managing those, ensuring that your companies, that your employees are skilled both on the floor as well as in the back end to be able to meet those requirements. I think those are kind of the 2 core pillars.
Thank you.
Okay, thank you, Marua. We have to move on to the next presentation. The next one on the agenda is going to be given by Lei Ren from Beihang University. The topic is AI frontier in industrial internet. Dr. Lei Ren is a professor with the School of Automation and the School of Software, Beihang University. He is the first recipient of the National Science Fund for distinguished young scholars in the field of industrial internet in China. He is one of the core contributors to the first theoretical and technical system, the first prototype system, and the first national standard in the field of industrial cloud manufacturing. He has presided over more than 20 national projects, such as the National Key Research and Development Program, the major research program of National Natural Science and the Foundation of China. He has chaired or participated in more than 10 international national industrial standards. Without further ado, I would like to ask Lei to present your talk. Lei, the floor is yours. Jesus. Are you online?
Yeah.
Yeah, please go ahead.
Hello, everyone. This is Professor Lei Ren from Beihang University. I would like to thank the invitation from Professor Li Hui Wang and really appreciate this opportunity to give a report here. The topic of my report is AI frontiers in industrial internet. And I will proceed my report in accordance with the following contents. Artificial intelligence has many practical implementations in manufacturing processes, which are divided into 5 phases in product lifecycle. And we list a few typical applications in each phase. First, in research and development, AI model is capable of generating design scenes in 2 or 3 dimensions for designers to work on. Based on previous design schemes, historical operational data, process knowledge, and customization, AI model can also recommend or even automatically generate design schemes for designers. Secondly, in manufacturing phase, AI models have been applied in autonomous control, manufacturing process optimization, dynamic scheduling, intelligent decision-making, and so on. Thirdly, in product tests and experiments, AI model is able to automatically generate intelligent test schemes and evaluate task metrics from experiments. Fourth, resources in manufacturing processes will be managed intelligently to further enhance production, and AI combining blockchain can be utilized for smart contract with higher privacy, security, and trustworthiness. Finally, in service and maintenance, AI models have been applied in predictive maintenance and intelligent diagnosis for products and equipment. Then a few works associated with following different kinds of intelligence will be discussed. Next part is industrial edge intelligence. Here is one work about industrial edge intelligence. In many complex equipment maintenance scenarios, a huge amount of sensor data need to be processed timely by edge devices with limited computational resource. Therefore, a novel dynamic lens architecture for industrial edge intelligence is proposed to adaptively learn sequence feature representation of different lens conditions on each sample. In our method, easily predicted samples are calculated by upstream network with a part of the sequence, and the other subsequent networks are unused. However, for those samples hard to predict, if upstream network provides an unconfident prediction, complete time series will be used for prediction. Abandoning the computation implemented in upstream subnetworks is highly inefficient, though upstream subnetworks are conducted with short sequence, which are trained for the same target and have learned beneficial information for remaining useful life prediction. Therefore, to utilize the information, feature reuse mechanism is proposed for better performance of RUL prediction. In this work, experimental results indicated that despite a difference in performance and datasets, both dynamic models can speed up with minimal accuracy degradation or better performance. Therefore, it can promote industrial edge intelligence with limited computation resource of the edge devices. Next, moving on to the cloud edge collaborative intelligence. I'm going to introduce two works in this part. The first work is a cloud edge lightweight temporal convolutional network, which can be called LTCN. There are several challenges associated with edge or cloud-based industrial AI. The first is meeting both accuracy and effectiveness simultaneously. The second is that we have to support complex industrial AI models with limited computing power at the industrial edge. And the third is potential decline in the performance of industrial AI when working condition changes in our industrial production. In this work, by combining cloud edge computing with AI technology, a data-driven method for RUL prediction is proposed. First, to meet the real-time requirement, a cloud edge computing and AI-based framework for RUL prediction is presented. Second, a new model structure named a lightweight temporal convolutional network is proposed and applied in this framework. Real-time prediction results will be obtained in edge plane, and higher accuracy prediction results will be obtained through historical information in the cloud plane. And thirdly, an incremental learning approach based on the updating partial parameters of LTCN is discussed to improve the accuracy of prediction models with newly collected data from equipment plane. The framework consists of three parts: equipment, edge, and cloud plane. The industrial equipment data will be generated and collected constantly in the equipment plane, and the prediction results will be both obtained in the edge and cloud plane. The model parameters will be updated through the incremental learning module in the cloud. Based on PCN, we propose a network structure named LTCN with fewer parameters and higher processing speed for regression tasks to improve our efficiency. The incremental learning method is used to obtain the updating parameters of the prediction models and a new training set without having to recompute that of the original models. After the training process, the selected subset of existing model parameters will be uploaded to the cloud. And experiments demonstrate that our Cloud Edge LTCN can improve the prediction accuracy and computing time of RUL. The second work in this part is label split multiple inputs convolutional neural network. Due to the increasingly complexity of the industrial processes, data obtained from a single industrial edge is usually of low quality, including unbalanced data, unlabeled data, and unseen data. Therefore, we propose a Cloud Edge collaborative method for adaptive fault diagnosis with label sampling space enlarging, named LMCN. First, a multi-attribute label sampling space enlarging approach is proposed to extend the variety of diagnosable faults. Second, a multi-input, multi-output data augmentation method with label coupling weight sampling is developed. In addition, multi-edge collaborative industrial AI framework is proposed. Specifically, a neural network is with a multi-input, multi-output configuration. The number of resampled samples can be an exponential multiple of the original. So data aggregation is a data enhancement method. Meanwhile, since it is a resampling method, it is not affected by the data imbalance practice. This configuration of neural networks can deliver examples for free. And with only a small increase in computation, discrepancies among various faults can be captured easily. So we propose a method to enlarge label sampling space by describing each sublabel. So some faults lacking of data can be predicted. The correct rate of prediction after label split is higher than the original one due to the coupling between sublabels. And pre-training fine-tuning approach is considered. The differences between faults are captured in pre-training, and in fine-tuning, the correlations between faults are explored to capture the differences within sublabels. And the experiments demonstrate that our method can effectively dealing with the unlabeled data. Then I'm gonna talk about industrial data-driven intelligence. The first work in this part is called MCTAN, which stands for the multi-channel temporal attention-based network. MCTAN is proposed for industrial health indicator prediction, which can weigh contributions of different channels through the channel attention. Then weight mean square error loss function, differently dealing with early predictions and delay predictions. By setting dynamic weights is presented to reduce delay predictions. And next, to deal with above mentioned issues systematically, a framework combining data pre-processing and MCTAN collaboratively is introduced to predict industrial health indicator through multi-channel time series. Different channels have different contributions to the health indicator predictions. The contribution of different channels is less considered in the field of industrial health indicator prediction before. The channel attention is applied before time series embedding to weigh the contributions of data from different channels and to avoid the loss of temporal information caused by averaging along the time scale. A learnable weight is used to obtain each channel feature along the time scale. The experiment in this work shows that the effectiveness of our channel attention mechanism and the local attention mechanism in our work, and compared with other methods, MCTA also obtains highest prediction accuracy and is able to significantly reduce delay predictions for all the subsets. The second work in this part is called long short-term memory deep factorization machine. Most existing model only analyze and model a specific characteristic of industrial data and cannot achieve fusion learning of various industrial data characteristics. But complex industrial data have diverse characteristics, nonlinear relationships, and massive unlabeled samples. Therefore, a data-driven self-supervised LSTM deep FM model is proposed for industrial soft sensor, in which a framework mainly including pre-training and fine-tuning stages is proposed to explore diverse industrial data characteristics. In the pre-training stage, LSTM autoencoder is first unsupervised pre-trained. Then, based on two self-supervised math strategies, LSTM deep can explore the interdependencies between features as well as the dynamic fluctuation in time series. In the fine-tuning stage, relying on pre-trained representation, the temporal, high-dimensional, and low-dimensional features can be extracted from the LSTM deep and FM components respectively. Specifically, we utilize unsupervised and self-supervised methods for feature generation. Multi-dimensional time series are masked and reconstructed with LSTM autoencoder to learn the serial correlation and inter-feature correlation of data, so as to improving the robustness of the model to missing elements. In addition, we use the aforementioned LSTM autoencoder as a pre-trained encoder. A deep FM model is constructed to mine the structural and non-structural correlations of the data and predict the final key indicators. And experiments on real-world fluctuation datasets demonstrates the effectiveness and superior performance of the proposed approach. Now, I'd like to move on to the industrial digital twin intelligence. As we know, robotic grasping is one of the most essential and fundamental operations applied frequently and widely, especially in unmanned industrial production. Grasp scenes become complicated and variable due to geometric and categorical differences of objects, bringing up challenges for the intelligent visual perception. Therefore, a digital twin robotic system is proposed to generate a synthetic grasp detection dataset composed of industrial parts only. And normal deep learning method is proposed to realize end-to-end 7 degrees of freedom grasp detection. Additionally, a continuous learning strategy is proposed for grasp pose detection to prevent catastrophic forgetting seen objects when learning grasping novel ones. As for objects in dataset, we select real industrial parts in categories, including actuators, damper, and roll die with complicated geometries compared with those domestic objects with relatively easy geometries. Every object is annotated with 1 kilometer grasp pose and corresponding grasp quality scores at object level. Then we generate amounts of virtual grasp clutter scenes to support the continuous learning task among various categories of objects. And we replace known objects to novel ones and repeat grasp scene generation process for more virtual scenes. The model we proposed for grasp detection is a two-stage model, which takes a point cloud of scene as input and detects several 7-degree of freedom grasp poses in the first stage, and rates and ranks all grasp poses in the second stage for grasp execution eventually. A continuous learning strategy combining rehearsal and regularization strategies is proposed for adaptive grasp detection in variable scenes with novel objects while preventing catastrophic forgetting. Finally, our detected grasp poses will be validated in virtual world for more stable performance. Then we will implement them in real world. Experiments have proved that our model generalizes industrial parts with various geometric contours and dynamically adjust to scene changes in industrial flexible pipelines. The consistency of performance between the virtual and physical world is also validated to demonstrate the effectiveness of our digital twin robotics system to deal with problems in industrial application. Besides, the combination of our model with digital twin system is suitable for lifelong continuous learning in industrial flexible production. And finally, I will conclude with towards future industrial big model. With prevailing trend of artificial general intelligence in recent years, many big models have demonstrated remarkable capability in many aspects. So it is really promising to integrate big models with manufacturing to promote our production in future. As we conceived, industrial big model is capable of solving any problem in manufacturing. And in condition to large amounts of data, large amounts of tasks that industrial big model can perform, big models still have to generalize on various scenarios and domains. Therefore, it is significant to study domain adaptation to address the problem of domain shift, which industrial big model may suffer from. This is our first work on cross-domain model named the temporal frequency attention transformer. Time series extrinsic regression aims at predicting numeric values based on the knowledge of the entire time series. The key to solving this problem is to extract and utilize the most representative and contributed information from raw time series. With auxiliary task facilitating the primary task, our method performs a virtuous circle in optimizing regression model. And while trainer transformer encoder outputs a more accurate correlation matrix from which the most precise attention distribution can be estimated, so that the auxiliary task based on the attention mask become more conducive to primary task. In experiment part, we evaluated the performance of the proposed model on the 12 dataset of TSER problem under various application scenarios. Moreover, the comparison experiment and ablation study are carried out to validate the efficiency of our method. The second work in this part is meta-learning based domain generalization framework. Intelligent fault diagnosis model have demonstrated a superior performance in industrial health management scenarios. However, these models may struggle to generalize in complicated industrial environments when encountering new working conditions, with distinct distribution shift and handling low resource data, such as different label space. To cope with the aforementioned issues, we focus on constructing a universal training framework with domain generalization technique that will encourage fault diagnosis model to generalize well in unseen working conditions. First, A model agnostic meta-learning based training framework is proposed for homogeneous and heterogeneous domain generalization. Also, we propose a bi-level meta-learning optimization algorithm to optimize parameters of industrial fault diagnosis model, so as to avoiding the computation problem in higher order and optimizing our model to generalize well in unseen working conditions. In the experiment part, we evaluated the performance of the proposed model on PHM09 fault diagnosis dataset. It can be observed that our method has excellent performance and achieved superior results on a set of generalization tasks across various working conditions. In last work of domain adaptation called single multi-source black box domain adaptation, there are two main challenges. The first is that the traditional domain adaptation method often require access to source data or source models during training, which is unavailable in some fields because of privacy protection and the storage limit. The second challenge is that the current UDA methods have not considered the temporal consistencies and low signal to noise ratio of sensor time series, which have particular attributes different from images and text. Therefore, we design a temporal consistency loss by combining an adaptive mask method and dynamic threshold method to maintain consistent temporal information and balance the learning difficulties of different classes. For the multi-source black box domain adaptation, we further propose a shapely enhanced model to determine the contribution of each source domain. And the experiment results on both single source and multiple source domain adaptation shows that our framework has superior performance compared to other black box and source-free UDA methods. All right, that's all for my report. Thank you for listening.
Thank you. Thank you for presenting your work, especially different machine learning algorithm and different perspective towards the future industrial internet. Because of time, I will skip the Q&A part. And if there's any questions online and local in the room, please send us. We will channel it back to the speaker. Thank you, Lei.
Thank you.
Now we move on to the next presentation. The next presenter is Sylvain Kalinen, and he will present a research. The title is Research Challenges of a Programming Robot Using AI and Manufacturing for Manufacturing Applications. Dr. Sylvain Kalinen is the Senior Research Scientist at the EDIAP Research Institute and a lecturer of EPFL. He has the Robotic Learning and Interaction Group at EDIAP, exploring new applications of human-robot collaboration and robot learning from demonstration. The approaches developed in his group can be applied to a wide range of applications requiring manipulation skills with robots that are either closer to us, assistive or industrial robots, part of us, prosthetics and exoskeleton, or far away from us, teleoperated robot.
Thank you very much.
Oh,
thank you very much for the introduction. Yeah, I think it will be easier to move the slides.
Yeah, floor is yours.
Yeah, so thanks again. So yeah, so I come from the EDIAP Research Institute. It's a research institute in the Swiss Alps in Martigny. It's about 200 persons working in the field of AI and machine learning. The institute has been created in 1991. And from the beginning, it was around AI. So it was the main research topic from the beginning. And we have 16 research groups. We have a joint development plan with EPFL in Lausanne. And I'm heading the robot learning and interaction group. So what we do in our group is to think about manipulation skills for robots and to investigate different areas of robotics that require manipulation. And the one I want to talk about today is the one related to manufacturing. And the kind of robots that we target are robots for SMEs. So something that we realized is that when you have large manufacturing environments, the robots are usually programmed only once, and the robot will replicate very precisely the same movement again and again. And in this context, the robots are not reprogrammed. But in SMEs, we have a very different context and very different needs, because here the robots needs to share the same workspace as that of the users. And it also means that the robots will have to be reprogrammed much more frequently. And it's usually due to the number of products, the variety of products that you might have. It's also due to the small batch of products you need to consider. And let me try to hide this. No. Okay, maybe it will disappear if I'm not touching anything. So here what we need is new solutions to reprogram these machines so that the collaboration with the robots is efficient, and we adopt a user-centric way in order to provide tools to reprogram these robots. Checking if there is a way to make this thing disappear. Hide, okay, hide, floating, okay, perfect, okay. Okay, so to do that, we need to reprogram these machines, and the user-friendly way of doing this is to let the robot learn by imitation, because it's the way we are using when we are teaching ourselves different skills. We are demonstrating the task, and we are learning from these demonstrations. So the goal is to use here AI to have a similar mechanism so that we can transfer skills to these robots in a user-friendly way, and without requiring these users to know about a specific computer language, but really doing it in a natural way. So behind that, there is AI. We need to collect data and to learn something out of this data, but it's a bit more than AI in the sense that machine learning is typically a problem where we already have a data set, we learn something out of this data set, and then we want to reuse the model that we learned. Here we have something that is more bilateral interaction, in the sense that we can also act on the system so that we can get better data to have the systems learning by reducing the amount of data being required. We can also play with the amount of learning strategies that we can use, because when we have this kind of interactions with the robots, we have different ways of helping the robot by either correcting some parts of the task, by potentially using several users with different expertise, so that one user could teach one aspect of the task and another user could teach another aspect of the task. So we have these different imitation learning mechanisms. Sometimes we call it mimicking when it's at the level of the actions, and sometimes we call it emulating when it's about understanding the underlying goals and copying the goals. And then we have a robot that can refine the task on its own. So we have a robot that can also try within a region that is provided by the user, and then having some self-refinement mechanism so that the robot could also improve on its own. So it's by combining these different learning strategies that we can also reduce the amount of data required to learn a task. In some way, it's a bit the same as a scaffolding process. You know, when you are constructing a house, you first need a lot of support. And while the construction is progressing, you can remove these scaffolds and remove these supports progressively. And at the end, you would like your house to stand on its own. So for the skill acquisition problem, it's a bit the same. You first need the user to be here, but progressively, when the robot is repeating a task again and again, then the user doesn't need to be here all the time so that the robot can help the user to achieve the collaborative task. So when we are collecting this demonstration data, and when we are reusing this demonstration data with the robot, it doesn't mean that we are just recording and replaying the exact same motion. If I'm showing to the robot how to lift up a box, what I would like is to have the robot being able to generalize this task to new situations. So here, new sizes of the box. But also potentially, I would like to change the robot. If there is a new model available, or if I want to change the company, then I would like to reuse the task that has been learned with one of these robots and to transfer this task to a new machine. And here you also need to have this generalization capability and to have this AI learning system that has understood what's the essential features about the task that makes it generalizable to other situations. So I will use this example as a way to highlight what we mean by learning from demonstration. And I'm using this kind of funny example with a robot that learned how to serve raclette cheese. So very Swiss example where we have here a cheese master who will demonstrate the task in order to correct the robot and do the task in a good manner. So in a good manner, it means here that you need to combine information about forces and motion in order to do it correctly. So what we have behind is a robot full of sensors that is aware about where it is in space. We have a user that can guide the robot by the hand, so a process being very intuitive to demonstrate some skill. And we have a force sensor also looking at how much pressure the user is applying to the cheese. So what we do here is that we collect several demonstrations. And here, when I mean several, it's like between 5 and 10. And the goal of having multiple demonstrations is to have the robot learning how to associate the size of the cheese together with the movement. Because in this kind of task, since the cheese is melting, then the movement needs to be adapted. And here, by providing these few demonstrations, the robot can understand how to make the relationships between the two. And you then have a robot that can reproduce the task again and again until the cheese is fully served. So here, to do that, it's a fusion problem. You need to combine different sources of information. One is about the force, one is about the dynamics of the movement to do the task. And later on, when you have fused these different sources of information, you get this resulting behavior that will adapt automatically to different aids of the cheese. So obviously, we don't do only that. So here it's more like as a way to advertise what we are doing. But now I will show a couple of research projects that we have been where we have exploited this strategy in order to transfer skills. And what I wanted to show is the underlying challenges in terms of machine learning and AI. So first, one of the challenges is that our data can be very varied. So we don't have only, let's say, position data. We have richer set of data. Sometimes it's in the form of orientation data. Sometimes it's in the form of ellipsoids when we're talking about manipulability, stiffness, or inertia measures. Sometimes it's in the form of trees and graphs that we would like to also learn. And sometimes it's geometric objects like planes, lines that we need to consider. So it's not only position, and it's not only at the articulation level, it's really these different sources of data to take into account. Then we have two kind of control strategies that we need to consider. One is related to anticipative behavior. Here we could also call it planning. It's about having a capability to anticipate what comes next. And on top of that, we have another control technique that is more reactive in the sense that when we have perturbations, we need a robot that can face these perturbations in a very reactive way. So to do it online without having to think too much about it. And here it's usually a research challenge to combine these two sources of information. And this is useful if you want to have a reactive robot that can adapt to new situations. So this is the typical kind of tasks that we are investigating in our group with moving objects on manipulation skills, where you have a robot that needs to pick and place objects, but in environments that can change. Okay, another challenge is that we would like the same robot to do multiple tasks, because in SMEs, we typically have the problem that we don't necessarily have a robot that will do a single task. We want to reuse the robot for a variety of manipulation skills. And here what we did is to try to see with the same robot, we wanted to investigate which range of manipulation skills we could consider while still keeping exactly the same robot. So we moved from something being very tiny, as here inserting a thread into the head of a needle. So something that is very small, and this robot is not supposed to have the capability to do that. But what we did here is to add sensing information with laser scans that was enabling the robot to correct the movement locally in a way so that the task could be fulfilled. So it's a bit the same as us. We are not very precise in the sense that if we are closing our eyes, we cannot do this task. Even making this with 2 fingers, we cannot do it well. But if we open our eyes, we can make these corrections. So here in this application, we're doing this kind of corrections by using a smart sensing solution. And then by taking the same bimanual platform, we wanted to see if we could lift bulky objects. So here in this case, the research challenges behind that is to use the shape of the robot to do this. And even if the objects are much bigger than the robot, we're investigating if we could use more than the gripper to do this, and to use actually the whole body of the robot to do this kind of task.
Perhaps they didn't share the screen to the online participant.
Yes.
Oh, this one should be this one.
Okay. So I'm sorry for the participants online then. Okay. Can we still do the... Okay. Okay. This other example is another way to cope with the limited actuation capability of the robot. If we don't have expensive sensors in order to locate where the objects are, there is still a strategy that we can use that is called ergodic control, that is actually to have the robot moving around the target until it finds the target to reach. It's also something that we do naturally as a behavior, like when we are inserting object into other objects, then we are doing this. And here the goal is to provide this capability to the robot, which goes beyond what is done in classical industrial setting. We have a robot that can search for the target in an online manner, and having this kind of wiggling motion that is helping to do this insertion task. Okay, so when we talk about learning algorithms, with robotics, we cannot only use learning algorithms, we also need an interface, especially if we want to have these learning algorithms being useful for the users. So we want the users to be able to monitor what is happening, to understand what is happening when they provide demonstrations, maybe to visualize these demonstrations, and also to potentially pre-plan if a robot can be used for a task to be achieved in an industrial scenario. So here on the left, you can see this as an example. If you have a desk, there was some manipulation task that maybe people were doing manually. It's good to see if the robot could be a good tool that could help the workers to do this manipulation task. And to do that, we are developing also mobile-based solution with smartphones as a cheap interface that can be used to evaluate the feasibility of a robotic solution, and also to program the robots, so to help at programming robots by first generating the movement on a virtual robot, visualizing what will happen, and when we are happy with the task that we have programmed, to run it on the real platform. And all of these tools are really user-centric in the sense that they are using, I would say, like interfaces that people know already without having to relearn a robotic interface that can sometimes be quite bulky and difficult to use, and also without using more complex virtual reality setting that doesn't work well if you want to do that all day long. So here the augmented reality solution on a smartphone is the good compromise, I believe, between the two. The last application I want to show is the industrial and manufacturing applications where the user cannot be on site, either because it would be too dangerous, or because sometimes you want to have a teleoperation center being able to control several plants. So there can be these two situations, and it also depends if these plants or manufacturing environments are not accessible, which was the case here in this Dextrov project, because here we are talking about underwater equipment. So they have actually these valves to turn on the seabed, on the seafloor, and they want to do this from a teleoperation center because it's here very deep in the water, so it's nearly not possible to bring people there. So here what they did is to have this equipment in a virtual reality control center. And what they wanted from us is to have some AI technique that could let the robot on the other side automatically adapt to the location of the valves. So in some way, you can imagine here on the bottom, it explains what it is doing, but in a more, let's say, dynamic environment. Here you can see that on the right side and left side, the positions of the valves are not the same. But still, the user can teleoperate one of the robots on the left side, and the user doesn't need to care about the robot on the right side, even if the robot on the right side is doing exactly the same task, but with different locations of valves. So here in this case, the one on the right side is automatically adapting to these new positions. And this robot can do it in a non-line manner. So it means that for the case with the bimanual robot underwater, it means that if there are perturbations with the water, the robot will automatically recenter the arm in order to turn the valve without having the user knowing about this disturbance. So it means that from a user perspective, it's you don't need such a big concentration because you are just acting on a simpler environment to control the robot. So here it's just to advertise what we will showcase during the summit. So from tomorrow, tomorrow on Friday, we will have this robot that we will bring to the summit. It's a drawing robot, a portrait drawing robot. Some part have also been learned from demonstration. Here in this case, we taught to the robot how to hold the pen. So it means what range of variations is possible to hold the pen and still do a writing task correctly, and also how much pressure you need to apply on the paper to do the task well. So this is these ingredients we have taught those very intuitively from a set of demonstrations. And then later on, we program the robot to take a photo of a person, to extract the contour of the eyes, the mouth, the nose, and then to use a single pen to draw this portrait, and then having at the end like the person appearing, even if only one color has been used. And this is also something that we are showing if you have the chance to go to the Musée de la Main at Unilchuv. We have this robot being exhibited at it's an exhibition on AI, on the theme of AI, and it has been extended until the end of September. So yeah, so I hope I could convey the message that robots in manufacturers are not replacing people. They are tools empowering users, and there are a lot of applications that require this form of human-robot collaboration in manufacturing environment. Thanks for your attention.
Thank you, Sylvain. Very interesting talk. Yeah, go ahead. One question from audience.
Sorry, are you using generative adversarial network algorithms or?
So here I give a high-level overview about what we do in the group. So for the perception aspect, we are using neural networks. For the aspects where we have only a few demonstrations here, we are more situated, I would say, in machine learning techniques on running on only small amount of data, meaning that we cannot really use neural networks for that. So we're using other techniques that we also develop in our group related to tensor factorization and others, but here we don't have enough data to use to use this kind of techniques.
Have you tested this on any real-time applications where you might have latency issues?
So the latency issue is something very important for the control aspect. So we need to handle this latency issue. And here we are considering indeed like optimal control technique typically that can handle this latency issue. So in the field of control, it's related to model predictive control, for example. So in general, these applications, it's really requiring to have a diversity of research, I would say, from perception to planning to control on everything under the umbrella of optimization, machine learning, and optimal control.
Thank you. Yeah, that's another last question.
Thank you. Great talk. Thanks for that. I'm wondering whether you already have some thoughts around the interface between generative AI and robotics, especially relating to your use case where you're already providing some feedback through your mobile application. Whether you see in the near future that we're going to be able to use language to manipulate behaviors, and are you doing some work on this already?
Yeah, I think it's indeed highly important to combine language as also a way to explain or to discuss with the robot, because I mentioned there is this bilateral loop that is important to communicate with the robot to transfer skills. In our group, we didn't use language so far, but it's something that we are planning to do. And I believe it's something also really relevant that we should include in these techniques as also a way to describe what we are doing. So now we're talking about the demonstrations, not always, but sometimes you can really describe what we are doing. And it's good if we have language here to also speed up the learning process.
So if you have a further question, please visit the summit booth tomorrow. There will be more demonstration and explanation. Yes, thank you, Selvin.
Thank you very much.
So we move on to the next presentation. The next one is also remote, and presenter is Li Yuanjun Lai. The topic is on coding-based large-scale task scheduling for industrial edge intelligence. Yuanjun Lai is Associate Professor of the School of Automation Science and Electrical Engineering, Beihang University. She is a member of SCS, the Society for Modeling and Simulation International, and IEEE Robotics and Automation Society. She is also the Associate Editor of the International Journal of Modeling, Simulation, and Scientific Computing. She has won the Young Talent Lift project supported by China Associations for Science and Technology and the Young Simulation Scientist Award from SCS. Her main research interests are in the area of intelligent optimization, modeling, and simulation of manufacturing systems. Yuanjun, the floor is yours.
Hi, Professor Wang. Can you hear me?
Yes, please go ahead.
Sorry, I just share my presentation, but I disconnected, so I come back again. Thanks
That's
very much
uncertainty.
for your introduction, and thanks very much for Dr. Jing Cui's invitation. Today, my presentation is coding-based large-scale task scheduling for industrial edge intelligence. And let me start. Okay. I would like to share about is the task scheduling. So I will talk about job shop scheduling first. The job shop scheduling is a classic NP-hard problem, as we know. Before, a job defines a group of interconnected operations with precedence constraints. And each operation can be executed by one and only one machine. Each operation corresponds to a candidate machine list, and then the job shop scheduling problem refers to assign machine and the priority to each operation of the job to minimize the overall make span or the energy consumption. This kind of problem is usually solved by mathematical programming algorithm and evolutionary algorithms, or upcoming reinforcement learning algorithms. Suppose the number of operation is n, there are in total of two multiple n number of variable. N is usually 10 to 30 according to the scale of the machining process. In the when these jobs are submitted to an IIoT and industrial Internet of Things platform, things will be very different. Here comes to the Industrial Internet of Things, as Professor Leiden has just introduced. It closely connects manufacturing resources, suppliers, products, and customers with cloud and edge collaborative computing. A general structure of this platform is shown at the left side of my slide. At the top layer, Cloud Data Center provides abundant computing resources and storage for industrial data management and multidisciplinary knowledge extraction and complex computation and some cloud service. And the edge server in the second layer are distributed nearby industrial fields. These edge servers have limited computing ability and the storage volume. They can alleviate the pressure of cloud and make real-time supervision and control under the assistance of cloud. Because the supervision, control, simulation, and computing of these distributed production processes are located at the edge or at the cloud. And these tasks are interconnected to the and restricted by the underlayer manufacturing devices and some production lines. So there are two kinds of tasks to be scheduled in an IIoT-based manufacturing system. That is the manufacturing tasks and the computational tasks. A manufacturing task defines the machining or the assembly process which can be finished by production line or a workshop. In a general production scenario, each manufacturing task is further divided into a series of operations. These operations have strict precedence relationships and can be executed distributively by the different manufacturing devices. And to implement efficient production, each manufacturing task is usually accompanied by a group of computation, such as machining control, data sampling, numerical analysis, or digital twin simulation. In traditional manufacturing systems, these computations are deployed on OPC servers or PLC servers locally. This computation for one manufacturing task can be seen as a computational task, which to be offloaded to an edge or a cloud server. Therefore, a manufacturing task is usually associated with a computational task in the IoT platform. We make an example at this side. For example, suppose there are 6 machining tasks and 1 assembly task, six machining tasks and 1 assembly task. Each corresponds to a computational task. The first 6 tasks, we assume they are digital twin simulation tasks. And the last one is a data summarization task. So the manufacturing tasks have strict precedence relationship, but the computational tasks have different constraints. They may have start time constraints with precursor start. That means they can start if and only if their precursor starts. And they also have end time constraint with precursor finish. That means they can be finished only if their precursor tasks are finished. While the data summarization tasks have a usual start time constraint with precursor finish. That means it can be started only if their precursors are finished, just as the usual precedence constraints. So we can see the connection relationships between these computational tasks are very complex. There are 2 kinds of start time constraints and 1 kind of end time constraint. In addition, there are communication between the edge and the manufacturing devices. There are also communication between the edge servers and between the cloud and the edge. Therefore, the communication overhead among the computational tasks and the manufacturing tasks increase largely. That is also to say our problem is a communication intensive and constraint intensive problem. Nowadays, more than 79 million industrial devices are connected to IoT, and more than 3,000 IoT platforms are released by different enterprises, and more than 6.9 billion data are integrated. So that means more than 10,000 of computational tasks and manufacturing tasks which will be pulled to the IoT platform to execute. To solve this complex and large-scale problem, we establish a mathematical model. Let's start from problem modeling. First, we describe the complex precedence relationships between the computational tasks. We assume there are n manufacturing tasks, corresponds to n computational tasks. Each manufacturing task includes a group of operations that form a directed act-like graph, that is DAG. And also, computational tasks may also form a group of DAGs. But the precedence relationships include 3 kinds. That is, the start time precedent, the start time constraint with precedence start, and the start time constraint with precedence end, and the end time constraint with precedence end. 3 kinds. Then we come to see the variables. There are 4 groups of variables in this problem. For the manufacturing tasks, we are determining the manufacturing device to execute each operation and the priority of each operation. For the corresponding computational tasks, we are determining whether a computation task is executed in the cloud side or in the edge side. We are also selecting the computing servers to execute each computational tasks. Some research might say that why not separate this problem to schedule manufacturing tasks first and schedule the computational tasks afterward? That is because the start time and end time of the underlying manufacturing tasks, determining the start time and the end time of the computational tasks. On the contrary, the upper layer selection of cloud server or edge server determine the communication rate between the edge servers and the manufacturing devices. That is also because the restricted wireless communication bandwidth. So the upper layer selection of cloud server or edge server also decide the communication overhead between the edge and the manufacturing devices. A good scheduling solution for the manufacturing tasks independently may bring large communication overhead to one or more manufacturing devices. So we bring them together to form a large-scale scheduling problem. Then we start from calculating the execution time of manufacturing tasks. Let J be a manufacturing tasks, and each manufacturing task has an IM operations. The J's operation of the ith manufacturing task is OIJ. We assume a very simple precedence relationship between the NIM operations. That is, the first operation has no precursor, and the rest has only one precursor. That is, their previous one. That means OIJ's precursor is OIJ minus 1. Each operation OIJ is to be assigned to a device. If the device index is Xij, then we represent the device as DXij. And each device has a task queue. The queue including the time not to be executed and the task just assigned. So the start time of OIJ is the maximum time of maximum value of two terms. The first term is the end time of its precursors plus the transportation time. And the second term is the end time of the task executed in the same device queuing before OIJ. The end time of OIJ is the start time plus the processing time, which is predefined. And the end time of a task J is the end time of its last operation. Then we set the rated power of a device as PLD to calculate the energy consumption of manufacturing tasks. And the energy consumption is the execution time from the first task in the queue to the last task in the queue multiple the rated power, just as well as the setting in the traditional job shop scheduling. Then we come to see the computational task. A computational task can be described by 6 elements: CPU requirement, the memory requirement, the execution time under specific requirement, and the data from industrial devices. There is a device list and the communication overload list. This is determined by the selection of manufacturing devices and the underlayer manufacturing tasks. And there are also a description about the data required from cloud, maybe the trained model or some predefined knowledge, and the precedence task. The precedence tasks are divided into 3 kinds: the start time constraint with pre-start, the start time constraint with pre-end, and the end time constraint with precursor end. The basic constraints are also include the computational resource constraints. That means a task can be executed in a computing server only if its CPU and memory capacity at the start time are enough. And the second constraints are the maximum time to execute a task. If a task is allocated to the edge side, the sampled data from the underlayer industrial field, that is from the manufacturing devices which executes these NIM operations, is directly sent to the selected edge server. According to the 4G and the 5G communication rate computation formula, the communication rate between a manufacturing device and an edge server is determined by the connected devices to this edge server. And we should note that more devices is connected. To see the summation form, we can see that the communication rate is lower. That means if we select dense located manufacturing devices to execute the underlayer manufacturing tasks, and the nearby edge servers are limited, the communication rate between the devices and the edge servers will be very lower. That also means the edge server will connect more manufacturing devices, then the bandwidth divided to each device will be lower. But selecting far distributed devices will also bring high transportation time cost. So this is a conflict. It is hard to design a greedy heuristic to make a balanced and a low-cost decision for the previous manufacturing and the computational tasks simultaneously. After calculating the communication rate, the upload time from devices and the download time for cloud can be calculated. The start time is the maximum time that the precedence, that means the precursor tasks with the pre-start constraints have been started. And the precursors with the end pre-start constraints have been finished. And the first operation of the corresponding manufacturing task is started. The execution time is the maximum time of the upload and download, plus the basic execution time. And the end time is the maximum time of the three terms. The first term is the end time of the precursors with the end pre and the constraints have been finished. And the second term is the task itself is finished. And the third term is that the corresponding manufacturing task is finished. This is the end time. If the computational task is allocated to the cloud side, the sampled data from the underlayer industrial field is transferred by the nearest edge side to the cloud side. Then we face the same problem. If we allocated the manufacturing task to dense manufacturing devices, and these devices connected to the same edge server, then we will got a low communication rate. After calculating the communication rate, the upload time from devices can be calculated, and there is no downloaded time from cloud at all because the task is allocated at the cloud side. The calculation of the start time, the execution time, and the end time is the same as the calculation of the task time in the edge side. The energy consumption is determined by both the communication overhead and the computation overhead. Then we can establish a weighted objective function to summarize the overall mix span and the overall energy consumption from the industrial side and also the edge side. As we have introduced, it is hard to design a greedy heuristic to determine the value of each variable one by one, because each variables are affected by several precursors and the successors, and the manufacturing tasks and the communication tasks are interconnected, and influence each other. So introducing reinforcement learning algorithm to solve this problem is hard as well. One reason is that the interconnection among the tasks are too complex to design a suitable state and action space, and the reward function too. Another reason is that the problem scale is too big and the scenario varies a lot. Training a reinforcement learning model takes a large number of time and cannot extend it to new scenarios with different objective functions. Therefore, to search for a feasible suboptimal solution in a short time, we select the real number encoding to represent the 4 parts of variables. And we can apply general evolutionary algorithms to solve this problem with high randomness and dynamics. To make a diverse search, we first introduce the general evolutionary operators and the local search operators. We previously introduced the most commonly used simulated binary crossover, the polynomial mutation in real coding genetic algorithm, and the differential evolutionary operators and the ant colony optimization operators, the differential evolutionary mutation operators and the crossover operators, and the cuckoo search operators, and so forth. And we also introduce hill climbing operators, multi-dimensional hill climbing operators, and also permutation-based, like such like swapping and pre-inserting, post-inserting operators as well. We tried to make parameter configuration and the operator configuration for individual in each generation. Here, individual means and solution. In evolutionary optimization process, an individual represents a solution, and the individual is the solution with real number coding weight. And a group of individuals form a population. So we could keep updating the population iteratively to find a feasible suboptimum solution. So we can use hyperheuristic to assign an evolutionary operator and choose a parameter to generate a new individual based on the older population. During this process, we found that the random search operators for different individual in different problems landscape and different generation have similar formula. For example, the genetic algorithm and the differential evolution algorithm have similar formula, similar way of representation and operation, but they can obtain very different performance. So this inspired us to establish a coding-based evolutionary operator. Here is its presentation. Suppose the population of the G's generation is XIG. We will firstly do random shuffle to rearrange the population as X apostrophe. Then we let X0G apostrophe as the best individual we have found ever. Then we got n+1 random shuffled individuals. Based on these individuals, we got a new individual generation formula, XIG+1. The new individual is generated through the formula. The first term, omega XAG, is the base. The information of XAG is maintained according to the weight omega. A is the parameter we selected from X0 apostrophe to Xn apostrophe. Then we will got a gradient to update XAG. The gradient to generate an individual from XAG is determined by the second term. In the second term, K is a parameter to determine the number of gradient vectors applied to update XIG plus 1. Fi is a scaling parameter and the HPE is the Boole value in probability PE. It determines the probability of applying this gradient term. And the third term is a random term. Delta run means a random noise in the range of x min to x max. F2 is a scaling parameter 2, and the 1 minus HPE is the probability of applying this random term. So we can see that each time we could just select the gradient term or the random term just once, either of which. Then the fourth term defines the probability that the new individual turn back to the old ith individual XIG, just like the differential crossover operator. It's an rollback operation. With this formula, we can generate hundreds of operators with different parameters. In our algorithm design, we...
Sorry to interrupt you. Can you skip some of the detail? We are behind of time. Sorry about that.
Sorry.
Perhaps you can speed up a little bit.
Oh, sorry.
Yeah, you can skip some of the details, and otherwise we are 10 minutes behind the schedule. Sorry.
Okay, sorry. So in this form, we can generate different operators, and we can also choose different parameters to make an equivalent evolutionary operators such as the differential evolution operators and particle swarm operators. And in our algorithm design, we use only random strategy to generate an operator according to the coding-based scheme we have introduced previously. And in each generation, we generate a random operator to generate each individual. To further accelerate the evolutionary search process, we divide the manufacturing and the computational tasks into several groups and form a parallel scheme. Each group has the same number of computational and manufacturing tasks. And in the grouping process, we select the task with high communication overhead, and the ones corresponds to the same manufacturing devices to form a group. And we adopt a subpopulation to solve each of the subproblem. After a number of parallel evolutionary research, and we could do solution merge to generate a complete solution. There must be some conflict, so we could assign overloaded server. We could assign tasks in overloaded server or manufacturing devices to nearby cold spot server and devices. With these feasible complete solutions, we could apply generative coding evolution schema again on the complete solution to make fine-tuning till the maximum number of generation is reached. Then we make experiments on the 3 scales with 1,000 tasks, 1,000 tasks, 2,000 tasks, and 4,000 tasks in 3 scales. And we establish simulation scenarios established based on plant simulation and cloud sim. Here is the design of cloud sim class, and here is the design part of layout of our plant simulation layout. Then we could find out that the proposed coding-based operator with random hyperheuristic outperforms other basic algorithms to a great extent, but the execution time is more than 400 seconds to schedule 4,000 computational and manufacturing tasks. With parallelization, the time for generating suboptimal solution in the same quality is only 9 seconds. We use only random hyperheuristic to generate coding-based operators, and we use the simplest grouping way and the parallelization strategy. We use ring topology to make subpopulation interconnection to solve this problem. So we can conclude that there is still plenty of space for us to design a hyperheuristic to generate more efficient evolutionary operators and the local search operators to solve this problem autonomously with different objective function. And there is also plenty of space for us to design to accelerate the evolutionary process. Generate coding-based operators during the evolutionary search process, or make efficient grouping on hybrid tasks, or even generate suitable parallelization strategies to solve this problem quickly. This might be our next work to solve such large-scale complex NP hard. And this is the end of my presentation. Thanks for listening.
Thank you for the presentation, and sorry about my interruption. Do we have a quick question from the audience?
Okay, it's okay. Sorry about my problem.
Perhaps I can ask a very quick question. Do you think federated learning approach can help because you have a cloud server, multiple edge computing devices? Will the federated learning approach can help the efficiency?
Sure. Because I have found some related learning, not applying in this task scheduling problem, but other benchmark. We found Professor Yao Chujing has published some very good methods on the federated learning on the related evolutionary research problems.
Okay. Thank you very much. We need to move on. It's not your fault that we have accumulated delay. Thank you.
Thank you.
Let's move on. The next speaker is Ashraf Abushadi from UNIDO, and he will present successful practice derived from technical assistant project implemented in some developing countries. Ashraf is a senior advisor for digital transformation and AI, UNIDO. And he is a highly accomplished professional with a strong background in digital transformation and artificial intelligence. As a diploma engineer, he served as the senior advisor for digital transformation and AI at the Directorate of Technical Cooperation and Sustainable Industrial Development within UNIDO. Ashraf, the floor is yours. Whenever you are ready.
Yeah, sure. Thank you very much. We're just waiting just a few seconds for the presentation to be up. So thank you very much. So I will start with just a very quick introduction for UNIDO, because I think some of the people might not be really familiar with what UNIDO is. So UNIDO is the United Nations Industrial Development Organization, and it is the organization in the UN system which is caring for an inclusive and sustainable industrial development, mostly in developing countries and economies in transition. And just the two key words in here is inclusive and sustainable. And I think in relation to AI, we have to be really careful with the inclusion part. We have to make sure that all countries and all nations, and anyone who is interested can be included into the AI sphere. UNIDO has a mandate under the SDG 9 for industrial innovation and infrastructure.
对，磕巴的，讲到后面都有点感觉舌头不打转了，有点大舌头。
Remote participant, please mute your microphone.
因为讲英文的做了个
Can you mute your microphone remotely? Thank you.
All right. So UNIDO's vision is to promote a people-centric approach to digital transformation. As we have seen earlier from some of the presentation with the human-centric, this goes very much in line of what UNIDO wants to achieve, to have people-centric approach to digitalization and to AI in there. Taking from the business linkages to the connectivity, to the markets, to the value chain, to the SMEs, as we have seen before, we have to always put the human factor in there and try and assist as much as possible to make the linkages between all these different entities in there. We started a couple of years ago with the AI approach. We want to try to become the bridge to the fourth industrial revolution before jumping into the fifth industrial revolution. And I'm sure within today, tomorrow, and after tomorrow, we will be talking a lot about the fifth industrial revolution. But there are still some nations and some countries which need some assistance to get to the fourth before jumping directly to the fifth in there. We've conducted several projects under AI and digitalization. As a start, we have some projects for conducting research and documentation and guidelines. So we have to start from somewhere. We have actually done a project jointly with the ITU in 2021, trying to empower SMEs to not be scared, basically, from going into the 4IR technologies and to give them a sort of guidance for embracing in this journey. We have some automotive industry projects in Belarus, Colombia, Mexico, and in India, and it deals very much with automation and the use of robots and AI into that field. I think in Belarus, even we were assisting in the automotive truck, the self-driving huge Belas trucks in there. In Jordan, we just concluded the artificial intelligence strategy for the whole country in there, and it was already completed and implemented in 2022. And now we are in the phase of planning the projects that go under the AI national strategy for it. With the support from Japan, we have some IoT projects running in Kenya currently. We have projects under Global the Clean Tech Innovation Platform. We have some blockchain and smart lenses running in Africa. And the new field that we are tackling now is the precision farming and smart agriculture. And my detailed example, you will see that it goes deeper into this with using machine learning to identify specific species which are harmful to the agriculture land in there. This is another project that we have done in Venezuela. And this is the project in Namibia that I will be talking about in a bit more details. So basically, this is one area in Namibia. They have a problem with some kind of an invasive species in there. The invasive species takes over the land and prohibits them from either getting the grass to feed their cattle or to use it as a farmland. So we acquired some satellite imagery for the area in there. It's a type of Acacia mellifera. We have implemented drones into the area to get exactly the location of these invasive species. We correlated the data from the drones with the satellite imagery. You see these green dots in there are all this invasive species. So in 1 year, in 1 season, they can take over the whole grassland and start growing even further from there. The new predictive model that we have done is trying to take the indicators of the satellite images and use some kind of textual analysis instead of visual analysis. So it goes deeper onto the different layers that can be achieved with the satellite and transforms it into the texture, so it can easily differentiate between like water, plants, ponds, roads, grass, buildings in there. These are just some variables and enumerators for the model. We applied the model onto a larger area in there, and we were able to classify the areas where this invasive species is taking over mostly in the land in there. The second question that we needed to find out after we find it, what do we do with it? So you need to, with the help of Finland, got some initial funds. They built a small factory in the land in there, and they took this invasive species, they put it through the plant in there, and then it transforms it into coal and animal fodder. So you take the trunks of this plant and you transform it into coal under pressure, and the soft parts, the leaves and the thorn, and then you crush them and you make them into animal food in there. The issue is that we needed an incentive for the farmers to go and to collect actually these plants in there. So we needed to find a model to tell them, okay, if you go to this land in there, you can easily locate it. So we needed to give them the coordinates for these plants. And as an incentive, we thought if we can calculate the volume of these plants, then we can calculate how much coal they will get from this plant and how much animal fodder they will get if they cut the plants in there. So we needed to do another model for segmenting the tree crown to calculate the volume calculations from the satellite imagery in there. So these are just some of the results from refining the model to get the results in there and to separate the data. And all this is done in like 5-10 minutes to try and get the whole model running in there. So some of the tuning parameters that we had to use. The area is calculated automatically, the volume is calculated automatically, and the tree crown is calculated automatically from that model in there. These are just like some of the results that we had in there to calculate how many trees you can have in the field, how much savings you can have if you take this and put it to the factory, how much you will gain back again from, instead of losing your agriculture land to the invasive species. I mean, this is one of the models from the satellite imagery, so you can see that across the year, how much of the land has been lost for these invasive species in there. If nothing happens to them, they can easily take over the whole agriculture land in there. This is just a small animation across the years to just show again the invasive nature of this one. And if you look at the top right one, you see the factory that UNIDO has built in there next to the land. We've done some capture applications, some surveys to get more of the data in, a dashboard so that the farmers can use to locate already their farm, and there is a story map behind it. And now it's in the phase that it's waiting to spread, because we can take that model and we can go for the whole country in there to find the invasive species all across Namibia. Just to summarize at the end, the main goals for all this, for what we are trying to do, is just simply to put people at the core and engage into this digital. So now we actually have farmers in Namibia who, with a simple application, go to the field. They know exactly where the location of that tree that they need to cut. They cut that tree, they bring it back to the factory. They're using very simple digital applications, digital models, everything in there to try and bring them up to speed and coming up and make it easier for them to join all these industrial revolutions. So that's it for me. Thank you.
Thank you. Any questions from the audience? Yes, go ahead.
Thank you for a really interesting conversation. So for UNIDO as a central bridge of this AI adoption, are you concerned with the centralization of the compute powers in the hands of a few players like Google, NVIDIA? Because these large language models have increasingly more and more computational power. And have you thought about how to actually democratize this again, put it back to the people? Yeah, I know it's
That's
a very
very difficult question. I mean, it's really good question, but it's very, very difficult in there, because this goes back to the same question I was asking my colleague here about the cost versus the benefit for it. And that is a difficult question to answer. There is not yet enough, I think, research into this field to try and see, okay, you need to invest 1 billion to save 2 billion, or do you need to lay the ground for maybe an open algorithm that comes out and it's totally free of charge. But even if you have the computing and infrastructure power behind it, you still need to skill the people, you need to remove the fears, you need to check the legality of things. It is difficult. And this is where, in the beginning of my presentation, I was very focused on inclusion. We have to have somehow a mechanism to include these people in, even as a small start, to bring them up little by little in there. Thank you.
I can address that a little bit in that, you know, the governments are taking action and looking at this very acutely in terms of concentration of cloud computing power with 3 or 4 large companies. And then on the other side, you have, you know, like the G20, B20, the business side of G20, where countries are coming together to see, you know, how they can democratize a little bit more. So I think it will happen, but not at the speed probably that we anticipate.
One step at a time.
True. One app at a time. Thank you.
Great. I think UNIDO did much more work than industrial development. Great talk. So let's move on. The next speaker is Rumagard Nubler from ILO, which is the International Labor Organization. She will share with you new technologies, skills, and employment. By the way, you can present from here.
already copied in that. And
Okay,
Yeah,
so-
because otherwise the camera cannot see you. That's a blind spot over there.
Yeah, yeah,
I should stay here?
yeah.
Let me briefly introduce our speaker of today. Irmgard is a senior economist in the research department, ILO, International Labor Organization. She is a senior economist, and her current research program is focusing on structural transformation, technological change, and the impact on job, skill, and the future of work in both developing and developed countries. She manages research projects, undertakes technical work, and provides policy advice to ILO constituents in the area of productive transformation, industrial education, training policies, and on developing social capabilities for productive transformation. In previous capabilities in the ILO, she worked in the area of skill development, training systems, apprenticeship, and informal economy. Irmgard, the floor is yours. Please go ahead.
Thank you so much. Thank you for inviting me to this a manufacturing workshop. I apologize for coming late. I had some other meeting, but I think I came in time. I'm working in the ILO, which is after my colleague introduced so nicely UNIDO. Let me just very briefly explain you the background of the ILO, which was we are actually we were sisters and brothers. UNIDO and was originally, I think, the kind of branch of the ILO, as far as I understand, when there was the effort to diversify within the ILO. So the ILO was created in 1919 in the Treaty of Versailles after the First World War. And why that? In some way, we can say that the ILO was created or is as a result or as of the consequences of the huge impact of the Industrial Revolution on working conditions, poverty, inequality. And the First World War was also seen as, in some way, the result of all these inequalities and of social injustice. So the major mandate of the ILO is to create social justice for lasting peace. We have basically two approaches in the ILO of dealing with technologies. One is a labor market perspective. We are looking at the impact of technologies on employment, on skills. And the second approach is a developmental approach where we analyze how to manage and enable countries to harness SDI for sustainable development. And this is more the UNIDO approach. So in that sense, the ILO is also the main custodian of the of SDG 8. And my major current research project is about looking into how we can enable, in particular, developing countries and raise their capabilities to be able to harness SDI for progress in SDG 8. So today, my major message of my presentation today is I want to look a little bit back into history in order to put our debates a little bit in context of the last 200 years. Because we very often have these hype discussions, a new technology, and everyone is afraid of we are losing all the jobs. And there will be a lasting technological unemployment. My major message is, yes, technologies in the first wave destroy jobs, But technological change is not, you know, an incremental piece by piece, step by step process. Technological change comes in waves, and it comes in clusters. And this means in the first part of the wave, you have unemployment, but then you have adjustment processes. And in these adjustment processes, a lot of new jobs and employment is created. And I would like to explain that a little bit. So when you look at this graph, you can see that the employment to population rate between 1916 and 2015 of the OECD countries was basically increasing, which is the blue line. No, it's just the yellow. So because it's a relative data, you can see that in particular the share of women was increasing, was contributing to this increase. So we cannot see a falling trend, which would tell us, oh yeah, all these technologies since the 1960s has destroyed jobs. It simply does and did not happen. Next slide, please. So we looked at the few years ago when at the World Economic Forum, the report came out by Professor Schwab. Now we have the fourth industrial revolution. I don't believe in the fourth. I believe we are still in the first one. Because and then we had all these publications, and the robots will eat all our jobs, and oh my God. And so we just looked into, you know, what's really going on, and then you can see for the these are the for the OECD country. These are the, we looked at the data we looked at the robot intensity, the number of robots per 1,000 or 10,000 workers. And then you can see that this robot intensity is very different between countries. And these are the countries with the highest robot densities. And you can see this is the Republic of Korea, it's Japan, it's Germany, Sweden, and so on. And you can see that the green, no, the figure you see, it's the 2014 figure, and the little dash you see in the column is the figure of 2008. So you can see that there were some countries which had very high growth in robot density, others less. So when you then, next slide please, look into how the change in robot density correlates with the change in manufacturing employment in that period, then you can see, yes, there is a slight negative trend, but there is no, you cannot really say that those countries with the highest increase in robot density would have the highest decline in employment. And we're looking here at manufacturing employment as a share of total, I think, of total employment. So what you can see is basically the impact of a change in new technologies depends very much on the country-specific conditions, depends on the production and export structure. It depends on institutions, it depends on labor market issues, conditions, it depends on training, education systems, and so on. So next slide, please. And then you can also look at the, you know, what happens with the skill structure. And there was a huge debate about, I mean, every time we know that new technologies lead to the demand for more complex skills. And this time there was this debate, no, we have a polarization of skill structures. So we have, you know, an increase in the demand for low-skilled workers, a decrease for the demand in medium skills, and an increase for high-skilled workers. Again, when you look into the different countries, then you will see very different patterns of changes in these skill structures. Again, you know, in the United States, you can see that you had a decline in all three skills categories at the same time, and that was also the period when the United States had its major discussions about, you know, China, and when they realized what happens when you have globalization and you outsource too much of your production, then you just end up with a decline in these skills. And then you had some countries like Canada and Netherlands who had very small changes. And then you had, you know, countries like Italy or Germany, where you had some decline in low skilled, but, you know, an increase in medium and high skills. So it depends very much on your economy and the institutions and of society. Now, why does this happen? Like I said, there are several arguments, but there's one important, which is made by people like Carlota Perez. You know, she basically explains technological change as a wave, as an evolutionary process, and you have you know, in market economies, in capitalistic systems, companies compete in productivity. So there is a constant request for increasing productivity, and the direction of search for new technologies is to look for the technologies which increase productivity, and these are labor-saving technologies. So, and since this is why we have, since this first revolution, the Industrial Revolution, we have two major trends in technologies, and we always think it's God-given, but it's because it's happening in a capitalistic system. You have automation, which replaces workers, or you have a fragmentation of your production process, which started with, like Adam Smith explained, you know, within the factories, division of labor, then division between firms, then division of labor, or the division of in firms between regions, and finally we had the globalization, where we just had a global fragmentation of production processes. So it's built into the system that our technologies are labor saving, but you know, but what happened was, you know, these robots take on jobs which were dirty and hazardous, and they improve the quality and precision, and they're at lower costs and higher quality and so on. So in the short term, robots or new technologies are adopted in existing industries, and there it destroys jobs in the existing industries. So what's then happening is you have an adjustment process, because we have markets and we have societies. Economies are embodied in societies. And so when you have, you know, these new technologies in existing industries, what's happening is you have many negative side effects. Inequality is building up. You have more and more unemployment. So the institutions which you have no longer serve the purpose. Like you have, we often have the discussion, we have new technologies, and then the first reaction is, oh, we ban it, it's bad, you know. But it's not that we should ban it. We have to understand that we need new institutions, because the old ones don't fit anymore. So what's happening when you have these labor-saving technologies? On the one hand, you have market adjustments, That needs, of course, market institutions. When you have rising productivity, income, and demand for domestic products, that can kind of, expand. Your expanding demand can replace, can increase or compensate. And then what is important is, all these new technologies need to be produced. And that means you have a completely new capital goods industries, and that creates many new jobs and also more complex jobs. And the next one is, the market adjustment, but then you have societies, and you have a lot of, in sociology and other disciplines, you have a lot of literature on that, where like Karl Polanyi, who is, describing in his book, The Great Transformation, how societies respond to all these inequalities and injustice and poverty. And that leads then leads again to new institutions like reduced working time. The working time decline it's happened as a response to unemployment. When you have higher income, you can increase your demand, and reduced working time means you can, you have all of a sudden a leisure industry. All these sports, all these traveling, all that is it's part of this story. You have rising demand for R&D. So a lot of new jobs are created in the knowledge economy. You have a high demand for education. And then you have changing consumer behavior. All of a sudden, people ask for organic food, for craft beer, for artisan products. All this is a response, a social response to that. Next, please. Now I'm going very quickly to developing or emerging countries. Here the story is different, because in the emerging countries, in poor countries, where you don't have even electricity, you don't have to talk about the impact of technologies. But still, when you look at the robot density story, it's very interesting. Because these are now developing or countries with, rather low robot density. And you can see there is a big difference when you look at Asian countries, which are the green ones, which is like, look at China, which had in 2008 a very low, which is this bar, a very low robot density, but within very short time, to 2014, it had a huge growth in robot density. You have Malaysia, you have Thailand, so you had huge growth rates. But then when you look at Latin American countries, you see very low ones. So Puerto Rico, Argentina, Brazil, Mexico, they have very low robot density. So why is that the case? Next slide, please. The case is, this is basically, we explained that with the production structure. So when China was having this growth boom, Asian countries started to integrate into value chains because China was basically demanding intermediate manufacturers and natural products. So the natural products were largely provided by the Latin American countries, because they had these natural products. Asian countries, no, they did not have so much of that. So they specialized, and that was to some extent, also very smart. They've specialized on providing the manufacturing to the value chains. So these two countries had developed very different capabilities. Asian emerging countries build up capabilities to adopt technologies, to innovate, you have to learn to innovate. It's not something which is given to a country. And what happened in Latin American countries, they had already, Latin American countries had relatively high levels of the capabilities. Argentina was in the 1930s one of the richest countries in the world. So what happened was, for a long time, Latin American countries basically lost a lot of their capabilities to adopt new technologies, to innovate, to transform their economies. Asian countries had just built up this capability. So when all these robots came, the Asian countries were much more in a position to adopt them. And so what was, and you can see on this, sorry, can we just go back one slide? Yeah. So here you can, we have to find better, you know, what you can see is as a general trend is that in Latin American countries, manufacturing employment declined. And in Asian emerging countries, middle income countries, the manufacturing employment remained more or less stable. But you had some countries like Malaysia who had a deep decline in these jobs. Next slide, please. Now, what happened in Asian countries then, when the electronics industry started to boom, Asian countries were able to get a huge, to attract a huge market share. So about 75% of all the electronics production is in these Asian countries. And the Latin American countries, European countries, were not very successful in that. The electronics industry is one of the most robot intensive industries, in addition to car industry, the chemical industry. So the Asian countries benefited a lot, first from having already some capabilities to adopt industries, to adopt these robots. And so they could capture a lot of this growing market share. And in that process, they increased the robot density and the complexity of their economy, and they could also increase the number of good jobs. So based on that experience, there is now a lot of debate about this concept of windows of opportunities for middle income countries, that countries should prepare for new opportunities when new technologies emerge, so that they would be ready to adopt new technologies, diversify their production structure, increase the sophistication of their product structure, which means higher productivity, and that also, you know, means they have to look to enter industries with a high demand elasticity, so that you know, there's a lot of domestic and foreign demand. I would just like very briefly to, next slide, please, to talk very briefly about job quality, decent work on institutions, because this is a second important element of work in the ILO. Like I mentioned very briefly, new technologies often affect the quality of jobs and decent work. And for example, there is often a very unequal distribution of the benefits and the burdens and costs of technology. So we can, for example, observe that the wage share was declining for several decades now. So, you know, the productivity increase was shared in a very unequal way between labor and capital, which is now reflected in this rising high income inequality. Then we also have, so the ILO is doing research on that. Then we're doing a research on artificial intelligence and algorithm, and how this algorithm affects decent work and leads, for example, there's, you know, in many algorithms, there's a bias against, you know, against certain population groups, against women. It's a part of this. I'm sure you're familiar with that. Then there is an issue with surveillance and privacy. Employers increasingly use AI to survey their workers and to control them, which is against human rights. And then there are, as we know, there are some colleagues who are doing research on that, and they explore all these digital tools which are used by employers to manage the workforce at the workplace. And then finally, there is also research on life-work balance, you know, what happens with people, and when you sometimes are available 24 hours, 7 days a week, you know, there are people who constantly check the emails, who constantly respond to messages, and we see a growth in mental problems and burnout, and I think that is something which we need to be addressed as well. So the response of the ILO is, of course, we need new institutions, and we need an enforcement of international labor standards for decent work. Thank you so much.
Thank you for sharing different aspects. Any question from the audience? Yes, Thomas, right?
Yeah, thank you. Yeah, I think the question is more from the standpoint of a private citizen than from a researcher, because it's kind of political. So the mechanism you described in the beginning, that AI is a prospective major driver of productivity growth, and so there's a trend that in the beginning that usually drives people out of their original or their the work that they had, and they can move to other spaces. But isn't there the danger that if the system is just running its course, that the productivity gains are usually unevenly distributed? And is there a perspective on what could basically what could change that? Basically, like unionization of the world is probably a nice idea, but that is very like the trend is going in the opposite direction, right? So in every country, the unionization rate is going down, and so
it's reversing. It's the pandemic changed it. Yeah, I mean, it's basically the evolutionary approach. You know, Giovanni Dosi and Carlo Paris, all these people, Richard Nelson, Winter, all these people who say, you know, we have to understand that these are not market processes. You know, this innovation economics very much thinks about economics more in terms of, you know, market processes. And what they say is, you know, you have a very close interaction between technology, economics, and society. And you always have, and you know, growth models there is no society in growth models. There is no society in these market models. So what they basically say is, you know, you have kind of endogenous processes, and you know, companies look for new technologies, and then they innovate, but it's first a process innovation, you know, in existing, and then, you know, like you say, you have first some productivity increase, and then it's fading out a little bit, and we have all these debates now. You know, we had this, oh, where's the productivity? We have all this technology, but where's the productivity increase? But then you have all these negative effects. We all have it now, you know, high inequality, financial bubbles, institutions, you know, we're not happy with our institutions because, you know, we feel they don't serve the needs. So we have old, you know, we have some growth industries which are also, you know, fading out. So with all these crises, there is society's, you know, change, and these are learning processes which are induced by crisis, and then you have new social demand, you have new political demand, you know, and now we have, I mean, now it's very clear, the past 200 years of technological change created institutions like the ILO and international labor standards, which reconciled you know, growth with social goals. So when you look at like SDG 8, you have economic, social, and environmental goals. And that was a long battle of society. Of I mean, you had revolutions, you had the labor movement, they had the trade unions. They were fighting during the 19th century for reconciling that. But there was no agency for the environment. There was no one fighting for the environment. And the environment for a long time did not fight back like societies. But now it's fighting back. And now, it's only now that we start to realize, like we did it with this, reconciling economic and social goals, we have to now recognize that we also need institutions that reconcile economic, social with environmental goals. And I think, here the evolutionary economists say, you need a new thinking in order to make the transition from one phase, the process phase, into she calls it the golden age phase. It's then the phase of product innovation. Instead of applying technologies to existing products, people start to develop new goods, new services, new organizations, and that is where the phase where you have a lot of productivity increase, explosion of innovations. And she basically says the green, we have to think about the way, we have to develop a new vision on the way forward. And she said, of course, in our situation, it has to be a green vision. And if we move into that, that is now the chance to develop exactly such an innovation explosion to create new products, new jobs, and new wealth, but in a completely different paradigm. But that needs a fundamental change in our thinking.
Thank you. Thank you, Irumgard. Because of time, we need to move on. If you have any further question, please discuss offline. Now we move on to our last presentation of this workshop. It's going to be given by Thomas Sobotka. He is from Technical University, Vienna. The topic is on transforming industrial manufacturing for a sustainable future. Thomas is a senior researcher at Fraunhofer Austria Research Institute in the unit of production and logistics management, as well as in the TU Vienna Institute of Management Science since 2011. In his current research, he supervises a project for the simulation-based energy-aware optimization of production processes, production planning, and control in short to long-term planning horizon, and digital twin applications in production planning and control. He is the head of a research topic digital factory at Fraunhofer, Austria, aiming to develop solutions for reactive self-optimizing planning and control for production based on simulation-based optimization, IoT, sensor data, and AI method. Thomas, the floor is yours.
Thank you for the kind introduction. I'm going to talk about transforming industrial manufacturing for a sustainable future. And what I'm trying to tell you is, is some of the challenges for companies and for the industrial sector in that, how AI can play a role in the solution, and an idea of how to speed up the process or to facilitate the process more. Just so there's no confusion between it's Technical University of Vienna and Fraunhofer Austria will basically work in common. So I work for both institutions, and Fraunhofer is basically an applied research institution, always working closely together with the universities. And so we're basically, that means that we have quite a bit of industry exposure and a bit of insight, hopefully, into projects working with industry. Let me begin with a problem statement. So basically, well-known facts, but just to recap, the processing sector is contributing about 35% of the estimated global CO2 equivalent emissions. And that is mostly due to energy use in industry. And so this is basically the main mission statement also for us as an institution working in Austria with industry, knowing that the heavily industrialized countries are the major drivers for human-made climate change, and thus have the heightened responsibility to change something about that. And so there's the need to dramatically increase energy efficiency and flexibility for the production sector. So what we at TU Vienna and Fraunhofer see as a vision for that is moving towards a positive impact production. And what we mean with that is creating a manufacturing system that on the one hand does not emit and contribute to the bad things such as CO2 emissions and greenhouse gases, and on the other hand has a potential or has positive impacts on society, on the people working in or being implemented in the production process, in the manufacturing process, and also to not only look at CO2 and to forget about all the other things such as environmental protection as a larger field and water protection and such. And this basically aligns with the system of the Sustainable Development Goals, focusing on these which we've pointed out here, which are basically well-being for the people involved, and the energy system, and water and land use. So this would be the vision behind what's coming next. So just to brief that you get a brief idea of what this vision for the positive impact production is for us, that we are wanting to achieve sustainable well-being for people. So the achievements that the industrial system has brought to humanity, we want to have the good parts of that without with trying to mitigate as much as possible the bad aspects and creating good outcomes. So one would be moving towards a circular economy in manufacturing, transparency, or creating transparency tools to work towards that, researching technology and technology management methods, working with CO2 minimization through planning and control, working towards an ideal factory facility structure and technologies. Then the next thing would be it's positive impact, creating positive impact on society, and having a positive impact on a sustainable working environment. So these will be like a broad range of topics, and we'll want to focus on, we have to focus on priorities. And just this week, I heard Anders Levermann, who is a climate scientist and an IPCC report co-author, and he said, well, basically, we must stop burning coal, oil, and gas. And this is carbon that has not been in the atmosphere for a very long time. And he went on to say, oh, when we not do that at all, then we'll achieve something like 15 degrees temperature rise, which is kind of dangerous. And although he's researching tipping points, and he's well aware of that, he says there's no excuse, even if we reach tipping points along the way. At every step of the way, we can do something against what's still on the off ramp towards greater temperature increase. So as bad as it is that we reach tipping points, we still have to invest everything we can to not make it worse. So basically, CO2 neutrality in industrial energy use, and solution approaches. Well, very basically, this would be energy efficiency. So the amount of production output you get for the energy input, this has to be improved. So mostly by reducing energy input, because arguably production output is quite good as it is. And especially when we think about well-being of people, and not so much producing more, but producing stuff that improves health and well-being. And the other thing would be energy flexibility. And this would be, I'll come to the right-hand side, this diagram a bit more. It basically, for us, means synchronizing energy availability from green sources with consumption in industry. So this would be like both main goals we'll talk about in the next 10 minutes or so. So challenges on that way. So what we see here is a diagram of the current green energy share in Europe, and it's lower than we would like it to be, and it's especially low in countries such as France or Germany, which are heavily industrialized countries that don't have many traditional sources of green energy, such as water, and so we are there in the 20% region. In Austria, we have a bit more water and bioenergy, so we're at 33 or something. But those sources that are yet to be explored are not so much the ones we relied on thus far, but those are almost exclusively wind and solar. And so this introduces a whole new problem that the major share of the energy use in industry has yet to be transformed. And it's, for example, heat. For most industrial companies, that has to do with process heat that you need for heat treatment of materials, that you need for creating temperature for paint shops and all that kind of thing. And that is not right now running on gas, and it's a huge challenge to convert that to green energy. What this means in practice, we can see here. That's just from May, from first week of May, I think, of this year, a price curve from Germany, from the electricity market. And what you can see is that on a noon, somewhere in midweek, despite the electricity consumption being at the peak, the price was negative. So you get a negative price for using energy at that time. And that was because the green curve, the green energy was at its peak. And an opposite situation is here on the right, a very high price compared to that on a evening. I think it was 8 p.m. Where the sun is not shining, the wind was not blowing, and still we wanted to produce, and we wanted to light houses and whatever. And so what we think is, when we dramatically increase, and that we have to do, dramatically increase the amount of solar and wind in our energy system, and switch everything we have, or basically everything we have right now, from other sources to that, that increases or potentially increases this fluctuations in availability of the energy. And that means this price difference will increase. And so that's a factor that companies or the production sector has to deal with. So enablers. A key enabler for us would be AI-based optimization in the form of digital twins. And that is not to say that that's kind of an overlooked factor until now, because until now, energy efficiency and flexibility usually means creating better efficiency equipment that is better insulated and such, and all that is very, very important. We are not saying that this is not important, but we say that the next step, which is right now a bit overlooked, is the planning and control aspect of that. And that a key enabler there is AI-based optimization in the form of digital twins. Digital twin, just a quick touching base at what there are different definitions for digital twins. What we think of digital twins is we have a physical system, in this case our production, our factory, and we have our virtual representation of that factory, and it's fed by data, if possible real-time data, and what we then would have is a digital shadow, so basically shadowing everything the reality does, and we can use it for analysis purposes. And if we then continue the data flow back from this virtual twin to the real world system. Then we have the digital twin, and the digital side of it is for thinking ahead, basically. So thinking ahead and trying to find optimal solutions for reality that then can be implemented. And so control signals are then sent back to the real world to achieve that goal that has been thought of virtually in the virtual world. So digital replicas of the physical assets. So that's just the definition. And we can use that to drive energy efficiency in design of the systems, as well as in controlling. So basically two aspects, design and control of industrial systems. We can synchronize production with renewable energy supply and better maintenance of equipment, better use of equipment. How can this look like in practice? This picture is meant to show you how we see the industrial energy system from far above. So this would be, we have the production and we have the production IT, which would be ERP and MES systems. No need to go into much more detail there. Just what needs to be produced is basically in those systems. And all the data about the production system. And what we have traditionally is the grid supply of energy. And what we see now is that there's more to that. We can have local supply of energy. We can have energy conversion and storage. So basically buffering capabilities. And we can make predictions, weather forecasts. We know energy markets, for example, day ahead prices, for the next day on the electricity market, how much a kilowatt hour is going to cost you. And you can factor all that in within production. And this is where AI comes into play to consider those forecasts and data, to consider what needs to be produced, and then to come up with good solutions of controlling production, controlling the conversion and energy storage systems, and the local production systems. The goal: synchronizing energy supply and usage, designing optimized and flexible energy systems. So also using those systems to optimally design and size those systems, and working towards an automatic multi-criteria optimization. So basically, it's a very complex planning environment, and people need assistance, and AI and digital twins come there to the rescue, basically. It does not get human planners out of the process, but it helps them with processing this huge amount of information, and basically gives them something like an autopilot for the day-to-day decisions, so that they can focus on the tricky questions. Basically driving efficiency and costs, so the basic economic goals, combining those with energy and CO2 emissions goals. Just a quick look on an industrial demo. So basically we transferred this same picture into an industrial case. And here we have in the production process, which looked in the generic case like this. And now we have like this, we have three major equipments. We have, this is for a steel product, a producer. They are heating up steel slabs, basically, in a gas oven. Then they are doing heat treatment in various facilities that are today gas driven. And then they alternatively, for some products, use inductive heating and heat treatment. So, and what we do is we create the same system which we looked at before, created a digital twin, digital representation and optimization. And what we're doing there is we're basically right now enabling them to not only improve their current system and have a real-time system working with their production planners to improve energy efficiency. For example, if you do the correct order of stacking up or sequencing production orders according to in these heat treatment processes to increasing or decreasing temperatures, you save energy. That would be like a very basic example of what this optimization does. And we can also simulate variants that are not yet in the system, such as huge solar installations and storage options. And so we can beforehand test drive them with those companies and advise or find together the solutions that will work for them in the transition. So the proposed intervention now would be establishing learning factories that can help drive this solution into education and industrial practice. Using all those learning factories would be realistic environments where students and professionals can learn that and experiment and have this hands-on experience of the solution. Those learning factories can facilitate knowledge transfer and innovation and collaboration and connect industry and policymakers and academia. And they also can address the skills gap and prepare the workforce for this digital transformation. So yeah, the proposal would be creating a network of learning factories focusing on digital twins for the industrial energy optimization and developing a curriculum and best practices for teaching and learning in this field. So to show you just a very early stages proof of concept. So what we've done is just try to fail, how do we call it, fail fast, right? So to create something that works and iterate from there. We've just created a very miniature factory model that works a bit like a real factory with industrial process controllers and equipment, robots and all that. And we've added photovoltaic and energy storage capabilities, and we're basically demonstrating what we've demonstrated to you in a few slides back for the industrial case. We are doing on a very small scale packable thing, which we can do in a transport container that fits in any car. And we can drive to a university, we can drive to our industry events. And so this is like a first demo of how this can work. And so just to give you a brief insight into how this demonstration looks like. So for example, this tool or this digital twin says I have a weather forecast and I plan my processes accordingly. The sun is shining and now the clouds are arriving, and this digital twin reacts immediately. It says, okay, now the energy that I was going to produce in the next few hours, I can't produce. And so I should consider whether I should change my production plans or whether I should change the way I drive my machines. So a lot of systems have quite a bit of latency. And so it does not matter that much whether I produce or switch on this machine right now or in 15 minutes or in 20 minutes. And that could make a huge difference in terms of energy availability from renewable sources. And to know, knowing that and reacting to that in an automated way gives you great advantages. Just a quick afterthought, an additional enabler could be biological CO2 sinks that could either be used as just working in the best case as a natural forest that is organizing itself. So basically probably the best use case. So if we're thinking of building materials and construction materials, there's also a potential avenue for that we want to encourage researching. So basically using natural carbon sinks and then using it for building material. And also there, AI and digital twins can play a role in servicing and managing those, both the natural production and basically carbon sinking and also then the use of that. Just final thoughts, a brief view on the sustainable development goals. So this would mostly affect affordable energy and clean energy, industry, innovation, and infrastructure from our point of view, responsible consumption and production, climate action, and CO2 think. The CO2 think aspect would be concerning life on land. I'd like to conclude with 3 takeaways. So energy use and production is both a challenge and an opportunity for companies. So if we want to stay by or stand by our commitments, we have to make carbon use prohibitively expensive by 2030 something. And that means, yeah, companies or the industrial sector has to deal with that. And it's kind of the large green elephant in the room, that right now this cost pressure is not there. And companies have to work with the money they get from their investors responsibly, and so they cannot just invest in very far future, no matter what. So we creating this awareness and facilitating change in industry is very necessary, because more needs to be done. If we are looking now at the companies we work with, so all those goals for when do you want to be carbon neutral, and by 2030, whoever says the lowest number, if you look at their plans, they are sketchy when it comes to not all of them, but most. If you look at anything behind working with clean electricity, when you look at their process energy, which is like the most the major energy input in industry, the solutions are not yet clear. I mean, they are technically there, but how do we get there? And then it's kind of what I was talking about is not clear. And so it's very important that industry has this realization, and we can help industry realize that. And digital twins and AI can support this effort, as I hope to have shown. And learning factories could be a vehicle to increase that learning process. Yeah, thanks. It was kind of a wild ride through a bit of topics, but thanks.
Thank you, Thomas. Industrial transformation is another challenging topic of the day. We need to take care of this, move towards the future. Any questions? We are reaching the end of the workshop. If you have any
clarification. I actually presented about digital twins last time in March. But I like, one of the questions I had was around how you keep the data in sync between the between the virtual replica, the digital twin versus the physical asset.
Yeah.
And is it real time? And that is always the biggest challenge with DTs, right?
It can be real time. So in the example you saw with the miniature factory, there it is real time, because everything is controlled. And although it's industrial equipment, so it's FPC, SBS, industrial controllers, and all of that. But in most industry cases, until now, we don't think it's necessary for most applications to just get started. So, for example, we have companies working in food industry producing like this bacon or something. Those are processes that are many weeks of duration. There, it usually is, as a first step, okay to work to directly connect to the ERP system, which is basically doing the everyday operations, and the MES systems, so manufacturing execution systems, that are already in place, because it has to be like implementable, and then have this intelligence behind that just connected to it, basically receiving what needs to be produced, adding data concerning weather forecasts, adding data concerning energy markets, and then processing that, and then giving back the control information back into a realization. But it could be down to directly assessing the controller layer. But I think the better solution would be to develop the existing MES and process control systems that are there to work with intelligence, which we've just shown, so that we can work with infrastructure that is well developed in industry.
Okay. Any other question? No? From online, do we have any question from online participants? I see a red mark there, not quite sure. Is there any question I cannot read from distance?
No.
No question. Yes, go ahead.
Just for my clarification, is there any problems with just using storage as a solution to renewables? Because my understanding would be that with sufficient storage, all of this digital twinning would not be necessary. It would just be able to store enough.
it's about cost per unit saved, basically. And so the cheapest energy is that you don't use. So from our point of view is for example, the correct or the optimized way of controlling equipment so that energy is not used is the best solution we can have, because that's the cheapest kilowatt hour that we don't use. And once we reach a point where that's no longer possible, so we have optimized everything, then it's still a question of where do we invest, because storage costs not only like resources, and that equals money, and those resources also equal a CO2 footprint coming with them. So although, for example, if we talk about underground gas storage capabilities, those caverns that could be used for pressure storage or hydrogen storage, but all those things, they cost money and resources to build. So we have to maximize production of green energy, and then we have to, what we cannot help, then we have for that we have to produce storage capabilities. But everything that basically this optimization is virtual storage, right? So we are trying to avoid it as much as we can, and it would probably be necessary because like this planetary boundaries, and so we only have that much material, and so we want to live a good life, and so you know what we have to invest in certain things.
Okay.
Yeah.
Okay, thank you, Thomas.
Yes.
Now we reach the end of this workshop. I want to thank all the 8 speakers of today to sharing your perspective, your viewpoint with us. I hope this workshop helped us to better understand how to use AI to accelerate sustainable manufacturing, which is the main theme for this workshop. I also wanted to acknowledge the contribution from Jin Cui, who is the master to put this program together, take care of all the logistics and so on. Thank you. And also wanted to thank all the participants locally and remotely online. Please pay attention to the new announcement, perhaps sent to you by email regarding AI for manufacturing. This is one of the webinar series I'm coordinating and moderating. And please stay tuned. For those remote participants, please have a good day and a good night, depends on your location. And for the rest of us, enjoy the day and enjoy tomorrow's summit and the day after tomorrow. Thank you very much.
Thank you.